The sun has risen every morning of your life, every morning of every human life that has ever been lived. For 4.6 billion years, this luminous sphere has burned without pause, without flicker, without fail. It is the most reliable phenomenon in human experience, more certain than seasons, more steadfast than mountains, more enduring than oceans. We take this constancy for granted, the light that wakes us, the warmth that sustains the air we breathe, the gravitational anchor that prevents our world from spinning into the frozen dark. Yet tonight, we contemplate an impossibility, not to frighten, but to understand, to see, through the lens of what cannot happen, what actually is. The question itself seems absurd. The sun cannot explode tomorrow. Our star lacks the mass, lacks the mechanism, lacks any path towards such a catastrophic end. It is a yellow dwarf, stable and middle-aged, with 5 billion years of steady burning still ahead. But in asking what if, we open a window into the profound interconnection between our small lives and cosmic forces beyond imagining. Let the breath slow, let the muscles soften. We are embarking on a journey through physics and time, through light-speed delays and quantum mechanics, through the delicate balance that makes existence possible. This exploration invites the mind to drift across scales both intimate and incomprehensible, to rest in contemplation of forces that dwarf all human concern. The darkness of your room, right now, is filled with photons that left the sun 8 minutes and 20 seconds ago. By the time you perceive sunlight, it is already ancient history. The star you see is the star as it was, not as it is. This delay, this cosmic speed limit, becomes crucial in understanding what would unfold if our central star met an impossible end. So we begin, not with panic, but with wonder. Not with destruction, but with understanding. The sun that rose this morning will rise again tomorrow, and the day after, and for billions of days beyond counting. But by imagining its end, we come to appreciate the miracle of its persistence, the mechanism of impossibility. To understand what cannot happen, we must first understand what the sun is. Not the glowing disk we see from Earth, not the abstract concept of the sun, but the actual physical reality 93 million miles away. A sphere of plasma, 1 million times the volume of Earth, where 700 million tons of hydrogen fuse into helium every single second. The sun is not burning in the way a fire burns. There is no combustion, no chemical reaction, no consumption of fuel in any conventional sense. At its core, where temperatures reach 15 million degrees Celsius, hydrogen nuclei are pressed together with such force that they overcome their natural electromagnetic repulsion and merge. This fusion releases energy according to Einstein's famous equation, where a tiny amount of mass converts into an enormous amount of energy. 4 hydrogen atoms become 1 helium atom, and in that transformation 0.7% of the original mass disappears, converted into pure energy. This energy, in the form of gamma-ray photons, begins a journey outward through the sun's interior that will take thousands of years. The photons collide with particles, are absorbed and re-emitted, scattered in random directions, slowly working their way from the core to the surface in a drunken walk that defies straight lines. When these photons finally reach the sun's surface, they have been downgraded in energy, transformed from gamma rays to visible light and infrared radiation. They stream outward at the speed of light, crossing the void to Earth in 8 minutes and 20 seconds, carrying the warmth that makes all terrestrial life possible. This process is stable, remarkably, impossibly stable. The sun exists in a delicate equilibrium between 2 opposing forces. Gravity pulls inward, trying to compress the star into an ever denser sphere. The pressure from fusion pushes outward, trying to expand the star against gravity's grip. These forces balance perfectly, and have balanced perfectly for billions of years. For the sun to explode, this balance would need to catastrophically fail. But the sun has no mechanism for such failure. It is not massive enough. Stars that explode as supernovae are typically at least 8 times the sun's mass, often much more. These massive stars can generate the core conditions necessary for catastrophic collapse and explosive rebound. Our sun cannot. When massive stars exhaust their hydrogen fuel, they begin fusing heavier elements: helium to carbon, carbon to oxygen, oxygen to silicon, silicon to iron. Each step releases less energy than the last, and when iron forms in the core, fusion stops entirely. Iron fusion consumes energy rather than releasing it. The core loses its outward pressure, and gravity wins. In less than a second, the core collapses, rebounds, and unleashes a supernova that briefly outshines entire galaxies. The Sun will never reach this point. It lacks the mass to fuse elements beyond helium. When its hydrogen runs low, billions of years from now, it will expand into a red giant, swallow the inner planets, shed its outer layers as a planetary nebula, and settle into a long, slow fade as a white dwarf. No explosion, no supernova, just a gradual, gentle decline across billions of additional years. Yet we ask, what if? What if, through some unknown mechanism, some impossible physics, the Sun did explode tomorrow? What if the fusion suddenly ran away, uncontrolled? What if the star detonated with the fury of a supernova despite lacking any physical path to such an end? The question is impossible, but the thought experiment is instructive. By walking through the consequences, by following the chain of causation step by step, we come to understand the intricate web of dependencies that makes our existence possible. We see how fragile the balance is, how precisely tuned our cosmic circumstances must be. Imagine, then, that at the Sun's core at this very moment while you lie in darkness, something changes. Some impossible instability begins. The fusion rate suddenly accelerates beyond all equilibrium, beyond all control. The core temperature spikes, the pressure surges, the star begins to tear itself apart from within. This cannot happen. The laws of physics prevent it. The Sun's mass, its composition, its evolutionary stage, all conspire to ensure stability. But in this thought experiment, we suspend that impossibility. We allow the unthinkable to unfold so that we might trace its consequences across space and time. The explosion, when it begins, releases energy beyond human comprehension. A supernova produces more energy in a few seconds than the Sun produces in its entire 10 billion year lifetime. The core, where the instability starts, reaches temperatures of billions of degrees. Elements are forged in an instant. The periodic table created in the furnace of catastrophe. Gold, platinum, uranium, all the heavy elements that cannot form in normal stellar fusion, are born in this moment of violence. The shockwave races outward through the Sun's interior at a significant fraction of light speed. In seconds, it reaches the surface. The photosphere, the visible surface we see from Earth, is blown away. The outer layers of the star, millions of miles of plasma, are ejected into space at thousands of miles per second. And with this ejection comes light, unimaginable amounts of light. In the first second of the explosion, the Sun's brightness increases by a factor of billions. The star that took 8 minutes and 20 seconds for its light to reach Earth is suddenly pumping out enough energy to be visible from other galaxies, bright enough to cause shadows at midnight on planets hundreds of light years away. But here, on Earth, in this moment, nothing has changed. The Sun as we see it still appears normal. The light reaching us now left the Sun before the explosion began. The Sun we observe is the Sun as it was 8 minutes ago, stable and constant, giving no hint of the catastrophe now unfolding at its core. We have 8 minutes and 20 seconds before the new light arrives. 8 minutes before anyone on Earth's dayside sees the change. 8 minutes before the first indication that something has gone impossibly, catastrophically wrong with the star that gives us life. These 8 minutes become crucial. Not because they offer time to prepare, there is no preparation for what comes next, but because they represent the fundamental limit of causality in the universe. Nothing, not information, not gravity, not any physical effect can travel faster than light. The explosion is happening now, but its consequences are still in the future, racing toward us at the maximum speed the universe allows. In this brief window, Earth continues exactly as before. People wake, go to work, laugh with friends, worry about bills, plan for futures that will never come. The Sun shines normally because we are seeing its past. The present, the catastrophic present, is still hidden beyond the light-speed horizon. The Sun's gravity, like its light, propagates at the speed of light. If the Sun were to vanish right now, Earth would continue in its orbit for 8 minutes and 20 seconds before flying off into space. Gravity is not instantaneous, despite how it feels. We orbit the Sun where it was 8 minutes ago, not where it is now. So as the Sun explodes, as its mass is blown across the inner solar system, Earth continues its regular orbit around a gravitational centre that no longer exists. The planet has not yet received the information that everything has changed. We are living in the last moments of normalcy, the final seconds when the universe still makes sense. The fusion at the Sun's core is converting mass to energy at an impossible rate. In those first seconds of explosion, more energy is released than in the entire previous history of the star. This energy takes form as light across the entire spectrum. Gamma rays, X-rays, ultraviolet, visible light, infrared, radio waves, an electromagnetic pulse that carries with it the power to strip atmospheres, to sterilize worlds, to fundamentally alter anything it touches. But that pulse is still 8 light minutes away, racing toward us through the dark, carrying news of catastrophe at the maximum speed the laws of physics allow. The last normal sunrise. Somewhere on Earth, dawn is breaking. The sun lifts above the horizon, painting the sky in familiar shades of pink and gold. A person watches this sunrise, perhaps sitting on a porch with morning coffee, perhaps glimpsing it through a window on the way to work, perhaps not noticing it at all in the routine rush of another day. This sunrise is indistinguishable from billions that came before. The light has the same warmth, the same colour, the same gentle increase in brightness as the disk clears the horizon. The sun looks as it always has, stable and constant, giving no indication that 93 million miles away it has just torn itself apart in an explosion of unimaginable violence. The photons reaching Earth at this moment began their journey 8 minutes ago, when the sun was still normal, still stable, still the reliable star it has been for billions of years. These photons were born at the sun's surface in the photosphere, where temperatures hover around 5,500 degrees Celsius. They travelled through the vacuum of space, undisturbed and unchanging, carrying energy from a star that no longer exists. A child sees their first sunrise, eyes wide with wonder at the golden light. An elderly person watches perhaps their last sunrise, though they do not know it, appreciating the beauty born from decades of mornings. A night shift worker heads home under the rising sun, tired but satisfied with work completed. None of them know that this sunrise, this unremarkable sunrise, is actually the most significant dawn in human history. It is the last sunrise of the old world, the last moment when the future extends forward in a comprehensible line, the last time the sun is just the sun, familiar and safe, rather than an impossible catastrophe racing toward us at the speed of light. In 8 minutes, everything will change, but right now, in this precious window of ignorance, life continues with perfect normalcy. Birds sing their dawn chorus, responding to the light as their ancestors have for millions of years. Flowers begin to open, following the sun's warmth with a patience programmed into their genes across countless generations. The morning air warms slightly as more solar radiation reaches the surface. Across the world, people are at different points in their day. Where dawn breaks, morning routines unfold with practiced familiarity. Where the sun rides high in the midday sky, work continues, conversations happen, decisions are made about matters that will never come to pass. Where dusk falls, people transition toward evening, planning for tomorrows that exist only in imagination. Where night has settled, sleep comes easily, dreams untroubled by any premonition of the cosmic violence racing toward them through the dark. The sun as they see it, as we all see it in this moment, is a lie, not a deliberate deception, but a consequence of the finite speed of light. We live perpetually in the past when we look at the sky. The moon we see is the moon as it was 1.3 seconds ago. Mars, when visible, shows us its state from minutes earlier. The stars are ancient history, their light travelling for years, centuries, millennia before reaching our eyes. Usually this delay is inconsequential. The universe changes slowly on human timescales. The sun that was 8 minutes ago is virtually identical to the sun that is now, but not today. Today the gap between what we see and what is has become a chasm containing the end of everything familiar. The sun's apparent disk, as seen from Earth, subtends about half a degree of arc in the sky. This makes it appear roughly the same size as the moon, a cosmic coincidence that allows for perfect solar eclipses. but the sun's actual size is staggering. 1 million Earths could fit inside its volume. Its diameter is 109 times Earth's diameter. The distance from the sun's core to its surface is twice the distance from Earth to the moon. This enormous sphere of plasma contains 99.86% of all the mass in the solar system. Jupiter, Saturn, all the planets, moons, asteroids and comets combined make up less than 0.2% of the total. The sun's gravity dominates everything, holds everything in place, defines the architecture of our cosmic neighbourhood. When this sphere explodes, when its mass is blown into space at relativistic speeds, the gravitational centre that holds the solar system together simply ceases to exist. But Earth does not yet know this. The planet continues to orbit a sun that is no longer there, held in place by gravity from the past, waiting for causality to catch up. Imagine standing on that porch, watching that sunrise, coffee warm in your hands. The steam rising from the cup catches the morning light. A bird lands nearby, cocks its head, regards you with one dark eye before flying away. The sun climbs higher, clearing trees or buildings, and you squint slightly against its brightness. This moment is perfect in its ordinariness. Nothing feels wrong, nothing looks unusual. The universe presents itself as stable, as comprehensible, as continuing. And in a sense, it is still all those things. The catastrophe, while already underway, has not yet propagated to your location. You exist in a bubble of causality where the past still determines the present, where the future still extends forward in predictable lines. You cannot feel the explosion. No tremor in the earth, no disturbance in the air, no intuition or premonition warns you of what is coming. The sun's violent death throes happen in silence, because space is a vacuum and carries no sound. The electromagnetic pulse races toward you, but electromagnetic radiation gives no advance notice of its arrival. It simply comes, at light speed, without warning. In this moment, you're living in the last age of ignorance. The last time a human can look at the sun and see only the sun, not a harbinger of extinction. The last time the morning holds promise rather than doom. The last normal sunrise in the history of the world. And yet, even as the light from the exploding sun races toward Earth, some small part of the universe has already been affected. Light from the explosion has reached Mercury, the innermost planet, after a journey of just 3.2 minutes. The planet's sun-facing side is suddenly bathed in radiation, billions of times more intense than normal. Mercury has no atmosphere to protect it. The blast of X-rays and gamma rays strikes the surface directly, heating the rock to thousands of degrees in seconds. The side of the planet facing the sun begins to glow, to vaporize, to shed material into space. Minerals that were stable for billions of years suddenly undergo phase changes, melting, sublimating, transformed by energy that has no business being there. But Mercury's death happens in silence, witnessed by no one. The planet has no intelligence to observe its own end, no consciousness to experience fear or wonder. It is simply matter, responding to energy according to the laws of physics, transformed from a stable world into an expanding cloud of vaporized rock. From Earth, Mercury is invisible right now, positioned somewhere beyond the sun from our perspective. We would not see its destruction even if we were looking. The light from its vaporization must travel back toward Earth, adding to the journey time of the original pulse. Mercury dies alone and unseen, the first victim of the sun's impossible explosion. Venus, the second planet, receives the pulse after 6.3 minutes. Like Mercury, it has no one to observe its end, though its death is more complex. Venus has an atmosphere, thick and toxic, made mostly of carbon dioxide with clouds of sulfuric acid. When the radiation pulse strikes, this atmosphere becomes a liability. The dense air absorbs the energy, heating rapidly. The entire atmosphere begins to expand, to boil away, to be stripped from the planet by the force of the radiation. The surface, hidden beneath those clouds for billions of years, is suddenly exposed to direct radiation that would sterilize anything alive in microseconds. Not that Venus had life. Its surface, even before this catastrophe, was hot enough to melt lead. The planet's slow rotation, one day lasting longer than its year, means one hemisphere faces the sun while the other is in darkness. The lit hemisphere receives the full force of the blast, while the dark side remains momentarily protected by the bulk of the planet itself. But this protection is temporary. The expanding atmosphere, the debris field from the sun's explosion, the secondary radiation, all of it will wrap around the planet shortly, ensuring no part remains untouched. Still, on Earth, the sunrise continues its gentle progression. The sun climbs higher, shadows shorten, the morning warms. We have passed the 6-minute mark since the explosion began, but remain blissfully ignorant. The light reaching us is still pre-catastrophe light, still photons from the normal stable sun we have always known. In homes and cities across the world, life proceeds with its usual concerns. A mother prepares breakfast for her children. An artist works on a canvas, trying to capture the quality of morning light. A scientist in a laboratory puzzles over experimental results, seeking truth in data. A couple argues about something trivial that feels important to them. A dog barks at a passing car. A tree drops a leaf, ready for autumn despite spring having just begun. All of these moments, these ordinary slices of human existence, are precious beyond measure because they are the last such moments. The last breakfast, the last artwork, the last scientific inquiry, the last argument, the last bark, the last leaf. Everything is about to change in ways that make these concerns not just irrelevant, but impossible. The sun continues to climb. 7 minutes have passed since the explosion. 7 minutes of Earth continuing as it always has, held in orbit by gravity from the past, illuminated by light from a sun that has ceased to exist. We have 1 minute and 20 seconds remaining before the pulse arrives. In this minute, millions of heartbeats occur. Billions of thoughts form and dissolve. Life, in all its complexity and simplicity, continues to happen across the planet. A baby is born, taking their first breath, crying their first cry, entirely unaware that they have entered a world with no future. An elderly person takes their last breath, death coming from age rather than cosmic catastrophe, perhaps the luckier for having passed before the change arrives. Somewhere, a person looks up at the sun and wonders about it. Wonders about fusion, about the distance, about the scale of the thing that makes their world possible. They know the sun is large, know it is far away, know it is important. But the sun is so constant, so reliable, that it becomes wallpaper, backdrop, a thing taken for granted. Only in moments of conscious attention do we really see it, really appreciate the burning sphere that anchors everything we know. This person, looking up, shielding their eyes against the brightness, has no idea they are looking at the past, no idea that the present racing toward them contains nothing but light and death, no idea that in seconds, their wandering will be transformed into experience more direct and terrible than any wandering could encompass. The sun appears stable. It is not. The sun appears constant. It is not. The sun appears to promise another day, another dawn, another chance. It does not. 8 minutes have passed. The light from the explosion has travelled 93 million miles through empty space. It has crossed the orbits of Mercury and Venus, leaving vaporized worlds in its wake. It has passed through the asteroid belt between Mars and Earth, too diffuse to significantly affect those cold rocks. It has crossed the point where the moon orbits Earth, though the moon is elsewhere in its monthly journey right now. The pulse is about to arrive. In seconds, the light will strike Earth's upper atmosphere. In seconds, everything will change. In seconds, the last normal moment in human history will end. But right now, for these final seconds, we remain in the past. The sun climbs higher in its familiar path. The light is warm and golden and entirely normal. The world turns as it has turned for billions of years. And we do not know. We cannot know. We will not know until the information arrives, until the light from the explosion reaches us and transforms everything it touches. The last second ticks away. Sunrise continues, beautiful and terrible and utterly ordinary. Then the pulse arrives, and ordinary ends forever. 8 minutes and 20 seconds. The light strikes Earth's upper atmosphere at exactly the speed of light, which is to say at exactly the maximum speed at which causality can propagate through the universe. This speed, approximately 186,000 miles per second, means that when the first photons from the explosion reach the outer edge of Earth's atmosphere, 100 kilometers above the surface, the information they carry is instantly communicated to the molecules they encounter. These molecules, primarily nitrogen and oxygen at that altitude, suddenly find themselves bombarded by radiation billions of times more intense than normal sunlight. The photons are not visible light, not the gentle yellow-white glow we associate with the sun. These are high-energy gamma rays and X-rays, electromagnetic radiation with enough energy to strip electrons from atoms, to break molecular bonds, to ionize everything they touch. The upper atmosphere begins to glow, not with visible light at first, but with radiation across the spectrum. The air becomes plasma, superheated by the energy influx expanding rapidly. This expansion creates a shock wave that propagates downward through the atmosphere, compressing the air below it, heating it, transforming it. On the day side of Earth, where the sun is visible in the sky, people are about to see something no human has ever witnessed. The sun, that familiar disk that has looked the same for all of recorded history, suddenly changes. The change is not gradual. There is no slow brightening, no gentle transition. One moment, the sun appears normal. The next moment, it is billions of times brighter. The increase happens instantly from the perspective of any observer, because all the photons from the explosion arrive simultaneously, having travelled the same distance at the same speed. A person looking directly at the sun when this happens is instantly and permanently blinded. The retinas, designed to handle the sun's normal brightness, are overwhelmed in a microsecond. The cells that enable vision are destroyed faster than pain signals can reach the brain. There is no moment of seeing the bright sun, and then looking away. The looking away would need to happen before the light arrives, which is impossible, because there is no advance warning. But most people are not looking directly at the sun. Most people are going about their day, eyes pointed at books or screens or other people or the ground. These people experience the change differently. The world around them suddenly becomes impossibly bright, as if thousands of suns have appeared in the sky simultaneously. Shadows vanish. Everything is illuminated from the direction of the sun with such intensity that reflected light alone is blinding. A person standing with their back to the sun would see their own shadow not as an absence of light, but as a relative dimness compared to the overwhelming brightness everywhere else. And even that shadow would be bright enough to cause pain to look at. Materials begin to respond to this energy influx. Glass, suddenly heated by the intense radiation passing through it, starts to glow, then to melt. Plastics burst into flame. Wood begins to char. Paper ignites. Fabrics smoulder and burn. Metal surfaces become too hot to touch within seconds, then hot enough to boil water, then hot enough to glow red, then white. The air itself heats rapidly. The temperature on the day side of Earth begins to climb at hundreds of degrees per second. The heat is not coming from the air being warmed by conduction, but from direct absorption of radiation. Every molecule in the atmosphere is being hit by photons carrying enormous energy, and that energy has nowhere to go except into heat. People feel this heating as an immediate, overwhelming sensation of burning. Exposed skin blisters in seconds. The moisture in skin and eyes and mucous membranes begins to boil. The air being breathed is suddenly scorching hot, burning airways and lungs with each inhalation. There is no time to seek shelter, no time to move away, no time to do anything except experience the immediate, overwhelming transformation of the environment, from habitable to hostile. The atmospheric composition begins to change. Nitrogen and oxygen, the primary constituents, start breaking apart into individual atoms under the radiation bombardment. Some of these atoms recombine into different molecules. Nitrogen oxides form in vast quantities, creating a brown haze in the air. Ozone, normally found primarily in the stratosphere, is both created and destroyed in chaotic chemical reactions driven by the energy influx. The water vapor in the air, the humidity that makes tropical climates muggy and desert mornings crisp, begins to split into hydrogen and oxygen. This process, called photolysis, normally happens very slowly in the upper atmosphere, driven by ultraviolet light. But the intensity of radiation now hitting Earth drives it at an unprecedented rate. The atmosphere becomes a chemical reactor, with reactions happening thousands of times faster than any natural process. On the night side of Earth, where the sun is below the horizon, people experience something different but equally catastrophic. They do not see the sudden brightness, because the bulk of the planet shields them from the direct radiation. But they are not safe. The atmosphere, heated on the day side, begins to expand and circulate. Hot air rises, creating massive updrafts, and air from the night side rushes in to replace it. creating winds stronger than any hurricane. These winds, driven by the temperature differential between the day and night sides, reach hundreds of miles per hour within minutes. Buildings that survived millennia of normal weather are flattened, trees are uprooted, anything not anchored to bedrock is swept away. The night side, which might have been a refuge if it had remained calm, becomes a maelstrom of chaos driven by the catastrophe happening on the opposite side of the world. The ground itself begins to heat. Rocks absorb infrared radiation and warm rapidly. In deserts, where rocks are exposed to the sky, surface temperatures climb toward and past the boiling point of water. In forests, trees begin to smoulder and ignite, creating firestorms that dwarf any wildfire in recorded history. In cities, concrete and asphalt heat and crack, sometimes explosively, as moisture trapped in the materials flash boils and expands. Bodies of water respond differently. Water has a high heat capacity, meaning it takes a lot of energy to raise its temperature. The surfaces of oceans, lakes, and rivers begin to boil, creating vast clouds of steam that rise into the atmosphere. But deeper water remains cooler, at least initially. This creates a stratification, with a layer of steam and boiling water on top and relatively cooler water below. Marine life near the surface dies immediately. Fish are cooked in seconds. Plankton, the foundation of oceanic food webs, are sterilized. Whales and dolphins, rising to breathe, surface into air so hot it burns their lungs and skin. Those that remain submerged survive longer, but will eventually succumb as the ocean's heat penetrates deeper. On land, animals have nowhere to hide. Birds, flying when the pulse arrives, experience the sudden temperature increase and begin falling from the sky. Their feathers singed, their bodies cooked. Some die instantly, others suffer, falling to ground that has become hostile to life, unable to comprehend what has happened to the world that was moments ago their home. Large land animals fare no better. Elephants in Africa, bears in North America, kangaroos in Australia, all experience the same sudden transformation of their environment, from survivable to lethal. Their size, which normally provides thermal inertia, cannot protect them from radiation that penetrates deep into tissue. They collapse where they stand, their biology overwhelmed by heat and radiation damage. Smaller animals, creatures that might normally seek shelter in burrows or under rocks, find no refuge. The ground is heating, the air is heating, there is no cool place, no safe place, nowhere that the radiation cannot reach. Insects drop from the air. Rodents flee their burrows only to find the surface more hostile. Everywhere, on every scale, life encounters an environment that has suddenly become incompatible with survival. Plants, unable to move, simply stand and absorb the radiation. Leaves curl and blacken. Stems wilt. The moisture inside cells boils, rupturing cell walls, destroying the structures that enable photosynthesis and growth. Forests that have stood for centuries begin to burn. Grasslands become infernos. Crops in fields cook on their stalks. Humans, with our intelligence and technology, fare no better than other animals. Our buildings provide momentary shelter from the direct radiation, but they cannot protect us from the heating air, the failing infrastructure, the cascade of secondary effects. Power plants, dependent on cooling systems, begin to fail as the water they use boils away. Electrical grids overload and shut down as demand spikes and supply fails. Communication networks go dark as electronics overheat and fail. Those indoors, when the pulse arrives, might have a few seconds more than those outside, shielded by walls and roofs. But buildings are heating rapidly, becoming ovens. Glass windows, superheated by the radiation passing through them, shatter from thermal stress. Fires start in every structure as materials reach their ignition points. Fleeing outside offers no relief, because the outside is more hostile than the inside. People in basements or underground structures are more protected than those on the surface, but they face different problems. The air they breathe is heating. Ventilation systems designed for normal conditions draw in superheated air from the surface. Those who seal themselves in airtight spaces suffocate as oxygen is depleted. There is no good option, no survival strategy, no way to wait out the catastrophe. The human population, 8 billion people spread across continents and islands, experiences this transformation differently depending on where they are and what they're doing. But the ultimate result is the same. Within minutes, the day side of Earth becomes uninhabitable. Within an hour, as hot air circulates and atmospheric effects propagate, the night side becomes equally hostile. Within hours, every surface location on Earth is experiencing temperatures and radiation levels incompatible with human survival. Cities become graveyards, rural areas become wastelands, oceans become cauldrons. The biosphere, the thin layer of life that has covered Earth for billions of years, is being sterilized by energy from a star that no longer exists, and this is only the beginning. The initial pulse of radiation, devastating as it is, lasts for minutes or hours depending on the nature of the explosion. But the sun's explosion has other consequences beyond the electromagnetic radiation. The star's mass, blown into space, is racing outward as an expanding shell of plasma and debris. This material, while slower than light, is still moving at thousands of miles per second. It carries with it momentum, kinetic energy, and particles that will interact with Earth in new and catastrophic ways. The radiation pulse, arriving at light speed, is the warning shot. The actual impact of stellar material, the physical debris from the sun's explosion, is still hours away. Earth has been bathed in killing light, but the matter itself, the actual atoms that once made up our star, has yet to arrive. When it does, when that shell of plasma reaches Earth's orbit, moving at a significant fraction of light speed, carrying the kinetic energy of an exploded star, the effects will make the radiation pulse seem almost gentle by comparison. The electromagnetic radiation can heat and sterilize, can destroy infrastructure and kill living things. But the physical impact of stellar matter will fundamentally alter the planet itself in ways no amount of radiation could accomplish. We have 8 minutes of warning. We have used them unknowingly, living the last normal moments of human existence. The radiation has arrived, the day side burns, the night side faces winds and chaos, and still, the worst is yet to come, racing toward us through space, carrying destruction measured not in heat or light, but in raw momentum and mass. The sun has exploded, Earth has received its light, now we await its matter. And with that matter, the final transformation of our world from a living planet to a debris field orbiting nothing. The breaking sky. The atmosphere, that thin envelope of gas that makes Earth habitable, is coming apart. Not instantly, not uniformly, but systematically, from the top down, as the radiation continues to pour in from where the sun used to be. At an altitude of 100 kilometers, in the thermosphere where satellites orbit and auroras dance, the air is already gone. The intense radiation has imparted so much energy to the gas molecules that they have reached escape velocity, flying upward and away from Earth faster than gravity can pull them back. This region, normally so tenuous that it barely counts as atmosphere at all, has been swept clean, leaving an empty shell around the planet. Below this, in the mesosphere and stratosphere, the air remains but is transforming. Ozone, that crucial molecule which normally shields the surface from ultraviolet radiation, is being simultaneously created and destroyed. The high-energy photons split oxygen molecules into individual atoms, which then recombine into ozone, but those same photons also destroy ozone, breaking it back down. The net result is chaos, with the ozone layer effectively ceasing to function as a protective barrier. Not that the ozone layer matters anymore. The radiation now hitting Earth is so far beyond anything the ozone layer evolved to block that its presence or absence is irrelevant. It is like worrying about a screen door during a hurricane. The protection it once offered is meaningless in the face of energies it was never designed to encounter. The stratosphere, normally stable and stratified by temperature, begins to convect. Hot air rises, cold air sinks, and the orderly layers that define this region break down. This convection creates turbulence on a scale never before seen, with wind shears that would tear apart any aircraft unfortunate enough to be flying. Not that aircraft are flying anymore. Those in the air when the pulse arrived experienced simultaneous failures of electronics, structure, and crew. Computers fried by electromagnetic pulse, aluminum skin heated to failure point, pilots blinded or killed by the sudden brightness. Every aircraft in flight on the day side fell from the sky within seconds. Those on the night side had perhaps a few minutes longer, enough time to experience confusion and terror, but not enough to land or save themselves. In the troposphere, where weather happens and where humans live and breathe, the changes are most dramatic. The temperature is climbing rapidly, driven by direct absorption of radiation and by heat rising from the surface. Clouds are evaporating as the moisture in them flash heats. Rain, falling when the pulse arrived, turns to steam before reaching the ground. The convective currents being created are enormous, with updrafts and downdrafts measured in hundreds of miles per hour. The turbulence is so severe that it would be visible from space if anyone were positioned to watch from space, which they are not. The International Space Station, orbiting 400 kilometers up, received the radiation pulse before Earth's surface did. The astronauts aboard, looking toward the sun when it brightened, were blinded instantly. The station itself, its electronics shielded but not perfectly, began experiencing cascading failures. Solar panels, designed to convert sunlight to electricity, overloaded and burned out. Life support systems faltered. Within minutes, the station became a tomb, carrying its crew on a trajectory that will eventually decay and bring them back to an Earth that no longer offers any refuge. The water vapor in the atmosphere, normally distributed according to temperature and weather patterns, begins to behave strangely. In some regions, particularly over oceans, the humidity spikes toward 100% as surface water evaporates faster than it can precipitate out. In other regions, the water vapor is broken apart by photolysis into hydrogen and oxygen gas. The hydrogen, being light, rises toward the upper atmosphere where it will eventually escape to space. The oxygen remains, but as individual atoms or in unusual molecular configurations. This atmospheric chemistry, normally stable and predictable, becomes chaotic. Compounds that would never form under normal conditions appear briefly before being destroyed. The atmosphere becomes a laboratory for exotic chemistry, with reactions driven by energy levels that Earth's surface has never experienced. The smell, if anyone could smell it without their olfactory system being destroyed, would be acrid and chemical, like ozone and burning combined with sulfur compounds and nitrogen oxides. The atmospheric pressure at ground level begins to change. In some locations it rises as hot air is pushed downward by even hotter air above. In other locations it falls as convective updrafts create low-pressure zones. These pressure changes happen rapidly, faster than human ears can equalize, causing eardrums to rupture. Not that this matters to people already dying from heat and radiation, but it adds another vector of damage to the comprehensive destruction of the biosphere. Lightning begins to arc through the sky, not the normal lightning of thunderstorms, but something more chaotic and continuous. The ionized air creates pathways for electrical discharge, and the massive charge differentials created by the heating and chemical changes drive current through these pathways. The sky becomes a web of electrical arcs, some lasting for seconds, some for minutes, some stretching from cloud to cloud or cloud to ground or ground to upper atmosphere. These lightning strikes are not isolated events, but a continuous electrical storm covering the entire day side of the planet. The energy released is staggering, adding to the heat already overwhelming the surface. Places that are struck experience temperatures that vaporize rock, creating glass and plasma. The thunder, normally a distinct crack or rumble following lightning, becomes a continuous roar as thousands of strikes per second create overlapping pressure waves. On the night side, shielded from the direct radiation, the sky still shows the effects of what is happening on the day side. The auroras, normally confined to polar regions, spread across the entire sky as charged particles from the sun's explosion interact with Earth's magnetic field. These auroras are far more intense than any natural aurora, bright enough to cast shadows, shifting and swirling in colours that span the visible spectrum. The magnetic field itself is being buffeted by the solar wind, which has intensified beyond anything in Earth's history. The magnetosphere, normally extending 60,000 kilometers on the day side and forming a long tail on the night side, is being compressed and distorted. The boundary between Earth's magnetic field and the interplanetary field, normally at a stable distance, is pushed inward, allowing more charged particles to reach the upper atmosphere. This compression and distortion creates electrical currents in the magnetosphere and ionosphere, which in turn induce currents in the ground. Power lines, if any were still functioning, would experience surges that would destroy transformers and generators. Metal pipelines would develop voltages between different points along their length. Train tracks would carry currents that would weld switches closed. The electrical grid, already failing from overload and heat, receives another blow from geomagnetic induction. The radiation continues to pour in, minute after minute, not diminishing, but if anything increasing as different layers of the exploded sun reach Earth. The initial pulse was gamma rays and X-rays from the core where the explosion began, but now the radiation includes emissions from the outer layers of the Sun, which have also been heated to extreme temperatures by the shock wave passing through them. This radiation includes a higher proportion of ultraviolet and visible light, which penetrates deeper into the atmosphere than the initial gamma rays. The heating becomes more efficient, with energy being deposited throughout the atmospheric column rather than primarily at the top. The temperature increase accelerates. Surface temperatures on the day side, already hundreds of degrees Celsius, climb toward 1,000 degrees. At these temperatures, many rocks begin to melt. Lead boils, aluminum melts, steel begins to glow red. The infrastructure of human civilization, all the buildings and vehicles and machines built over millennia, begins to fail not from lack of function but from structural materials reaching their limits. Concrete cracks and crumbles as the water bound in its structure flash boils. Glass, already softening, flows like thick honey. Plastics burn away entirely, leaving only ash. Wood is long since gone, consumed by fire. What remains is primarily metal and stone, heated to the point where chemical bonds become unstable. The ground itself transforms. Soil, that mixture of minerals and organic matter that supports plant life, is being sterilized. The organic components burn away. The microbial life, bacteria and fungi and all the tiny organisms that make soil alive, die instantly when the radiation arrives. The mineral components begin to undergo phase changes, with clay minerals breaking down and reforming into different structures. In locations where the rock is close to its melting point, the surface begins to develop a glassy layer as minerals melt and resolidify. In volcanic regions, where magma normally sits kilometers below the surface, the additional heat is enough to trigger eruptions. Not because the magma is heated directly, the radiation doesn't penetrate that deep, but because the stress on the crust from rapid heating triggers existing instabilities. Volcanoes around the Ring of Fire begin to erupt simultaneously. Yellowstone's supervolcano caldera, dormant but not extinct, ruptures. The Icelandic volcanoes, the Mediterranean volcanoes, the East African rift volcanoes, all become active at once. The magma rising through the crust encounters an overheated surface and explodes out with violence enhanced by the unusual conditions. These eruptions add their own contribution to the atmospheric chaos. Ash and sulfur dioxide pour into an atmosphere already choked with combustion products and chemical reactions. The ash, normally a problem for aviation and local air quality, is almost irrelevant now. But the sulfur dioxide reacting with water vapour creates sulfuric acid, which begins to rain down on the surface. This acid rain, falling through superheated air, evaporates before reaching the ground in most locations, but in some places, where local conditions create slightly cooler zones, the acid reaches the surface and begins corroding anything it touches. Stone monuments, built to last millennia, dissolve. Metal structures corrode. The chemical weathering that normally takes centuries happens in minutes. The oceans, covering 70% of Earth's surface, are experiencing their own catastrophe. The surface layer, heated by direct radiation, is boiling. The steam rising from the oceans carries with it salt, creating a suspension of water vapour and microscopic salt crystals. This salty mist is corrosive, adding to the chemical assault on any remaining structures. Below the boiling surface layer, the ocean becomes stratified. Hot water sits on top of cooler water with a sharp boundary between them. This thermocline is far more extreme than any natural thermocline, with temperature differences of hundreds of degrees across a meter or less. The stability of this stratification prevents mixing, keeping the deep ocean temporarily insulated from the worst of the heating. Marine life that lives in the deep ocean, organisms adapted to crushing pressure and eternal darkness, are momentarily spared. They cannot see the sun, cannot perceive light, and the heat has not yet penetrated to their depths. For them, nothing has changed. They continue to hunt, to mate, to exist in the same way they have for millions of years. They do not know that their entire world is being destroyed above them, that the surface which they never visit has become hell. But their reprieve is temporary. The heat will penetrate eventually, conducted downward through the water column. The ocean currents, driven by temperature and salinity differences, will eventually mix the hot surface water with the cooler depths. And even if the deep ocean somehow remained cool, these organisms depend on food that ultimately comes from the surface, from photosynthesis and the rain of organic matter from above. When the surface dies, the deep will follow, starved rather than cooked, but dead nonetheless. The polar regions experience something different from the tropics and mid-latitudes. The sun, even after exploding, still illuminates Earth from its position in the sky. At the poles, during their summer when the sun never sets, the radiation arrives at a grazing angle, spread over a larger area. The intensity is lower than at the equator where the sun is overhead. But lower is relative. The radiation is still far beyond lethal levels, still more than enough to heat the ice caps and kill any life present. Antarctica, covered in ice up to 4 kilometers thick in places, begins to melt. Not the slow melting of climate change measured in decades, but rapid melting measured in hours. The surface ice sublimates directly from solid to vapor under the radiation bombardment. Below that, a layer of meltwater forms, lubricating the ice sheet and causing it to flow more rapidly toward the ocean. The Arctic, with less ice and more ocean, responds differently. The sea ice melts completely within the first hour. The ocean beneath, exposed to direct radiation, begins to boil. Polar bears, seals, walruses, all the megafauna adapted to the ice, find their habitat vanishing literally beneath them. They swim in water that is rapidly warming, seeking ice that no longer exists, until the heat becomes too much and they succumb. The atmospheric effects at the poles include unusual optical phenomena. The sun, low on the horizon, creates elongated shadows and refraction effects through the rapidly changing air. Multiple images of the sun appear, mirages created by the extreme temperature gradients. Halos and light pillars form and dissolve in seconds. The sky becomes a kaleidoscope of light, beautiful and terrible, witnessed by no one capable of appreciating it. All across Earth, in every environment, in every climate zone, the story is the same. The arrival of radiation from an exploded sun is not something life can adapt to, not something that leaves survivors, not something that creates niches where the lucky or well-prepared might endure. It is comprehensive, thorough, and final in its lethality. The timeline from the arrival of the radiation to the death of the last surviving organism on the surface is measured in hours, not days or weeks. Some bacteria, extremophils that can survive incredible heat and radiation, might last longer than complex life. Some organisms deep underground, in caves or aquifers, might be insulated enough to survive the initial pulse. But they are doomed nonetheless, because even if they survive, the world they emerge into will be sterile and hot, incapable of supporting any kind of food web. Earth's biosphere, that 4 billion-year-old tapestry of life in all its forms, is being erased. Every species, every individual, every cell and virus and prion, everything that could be classified as alive, is being sterilized by energy from a star that should have burned steadily for 5 billion more years, but instead has failed catastrophically, impossibly, taking its planets with it into oblivion. The sky itself, that dome of air and light that has sheltered life since the first organisms crawled from the ocean, is breaking. The atmosphere is not being stripped away entirely, not yet, but it is being transformed into something alien, something incompatible with any life that evolved under Earth's normal conditions. The familiar blue of a daytime sky, the black of a night sky, the reds and oranges of sunset, all of these are gone, replaced by a roiling chaos of light and heat and chemical reactions. And through this breaking sky, more radiation continues to pour in, unabated, relentless, carrying energy from an explosion that has already released more power than the sun's entire normal lifetime output. The explosion is not instantaneous. A supernova develops over seconds to minutes, with different layers of the star being expelled at different times. Earth is receiving not a single pulse, but a sustained bombardment, wave after wave of radiation, as the explosion continues to unfold 93 million miles away. Or rather, as the explosion unfolded 8 minutes ago, because we are still receiving only information from the past, light that left the dying sun and crossed space to bring us news of catastrophe. The explosion might be over by now. The sun might have completely disrupted, its matter flung across the inner solar system, leaving only an expanding cloud of plasma where our star used to be. But we won't know for 8 more minutes. The light from the end of the explosion has not yet reached us. We are living through the middle of a catastrophe, blind to its beginning and its end, able only to experience the present moment as wave after wave of killing radiation transforms our world. The silent cities. Cities, those dense concentrations of humanity and infrastructure, are dying in silence. The silence is not because nothing is happening. Everything is happening all at once, catastrophically, but because those who might scream or cry out are already gone, and buildings do not make noise when they fail. They simply crumble, melt, burn, structural integrity lost to heat and radiation. New York City, that vertical monument to human ambition, is collapsing. The steel frame of the skyscrapers, heated to hundreds of degrees, begins to sag. Steel loses strength as it heats, and at 600 degrees Celsius it retains only 50% of its room temperature strength. The buildings are being heated well beyond this threshold. The iconic skyline, recognized worldwide, is deforming as gravity pulls on steel that can no longer resist. The collapse, when it comes, is not like the controlled demolitions used to bring down old buildings. There is no careful placement of charges, no precise timing to make the structure fold into its own footprint. Instead, the buildings fail randomly, wherever the heat happens to be most intense, wherever the steel happens to be thinnest, wherever some combination of load and weakened structure creates a critical failure point. A skyscraper in Midtown begins to lean, slowly at first, as the steel on one side softens before the other. The lean increases, and the building's massive weight creates forces the damaged structure cannot withstand. It topples, falling across blocks of other buildings, crushing them, creating a domino effect of destruction. The sound, if anyone were alive to hear it, would be apocalyptic. But the sound travels through superheated air that distorts and absorbs it, and there are no ears to hear regardless. The subway system, normally a refuge during surface catastrophes, has become a death trap. Those who fled underground seeking shelter from the brightness found that the heat followed them. The tunnels running beneath buildings and streets are heated by conduction from the surface. The air in the tunnels with nowhere to go becomes superheated. The people who sought safety underground were cooked alive in the dark, dying perhaps more horribly than those who remained on the surface. The rivers, the Hudson and the East River, are boiling where they run through the city. Steam rises in enormous quantities, creating a fog that mixes with the smoke from countless fires. This fog is scalding hot, carrying more heat than the air alone. It flows through streets and into buildings seeking the path of least resistance, filling any space not already occupied by fire or collapse. Central Park, that green rectangle in the heart of Manhattan, is burning. The trees, planted and tended over generations, are ablaze. The grass has been incinerated. The ponds have boiled away, leaving only cracked mud that is itself heating toward the point of vitrification. The rocks, those glacial erratic boulders scattered through the park, are too hot to touch, would be too hot to approach, glowing a dull red in the brightest areas. The bridges connecting Manhattan to the outer boroughs and New Jersey are failing. The Brooklyn Bridge, with its iconic stone towers and steel cables, is sagging as the steel heats. The cables lose tension as they expand, then begin to glow as their temperature climbs. The roadbed suspended by these cables drops toward the river. Eventually the cables fail entirely, and the roadbed plunges into the boiling East River, sending up enormous gouts of steam. Similar scenes play out in every city on Earth's day side. London's ancient architecture, buildings that survived fires and bombs and centuries of weather, crumbles under heat they were never designed to withstand. Tokyo's earthquake-resistant skyscrapers, built to flex and sway, instead melt and collapse. Mumbai, Cairo, São Paulo, Los Angeles, all the great human metropolises, all the places where millions lived and worked and dreamed, are being systematically destroyed by energy from an exploded star. In Paris, the Eiffel Tower, that iron lattice structure visible across the city, begins to glow. The iron, heated by direct radiation and by conduction from the surrounding air, reaches temperatures where it emits visible light. The tower glows red, then orange, then yellow, a brief moment of terrible beauty before the structure weakens and collapses into a heap of molten metal. The Louvre, with its priceless art, is burning. The paintings, carefully preserved for centuries, ignite on their canvases. The colours run as paint melts. The Mona Lisa's enigmatic smile is consumed by flame. Sculptures crack as materials expand at different rates. Glass cases shatter. Everything that made the Louvre a repository of human cultural achievement is being destroyed, reduced to ash and slag, irreplaceable art vanishing in minutes. Rome, the eternal city, finds that eternity has an ending. The Colosseum, standing for 2,000 years, cracks as its stone heats and expands. The Vatican, with its treasures and libraries, burns. The Sistine Chapel's ceiling, Michelangelo's masterpiece, blackens and falls. The Pope, if he lived long enough to see it, would witness the destruction of the institution he led, the physical structures of the Catholic Church melting or burning across the entire world simultaneously. Moscow's Red Square is obscured by smoke and steam. The Kremlin's walls are cracking. St. Basil's Cathedral, with its colourful onion domes, is burning. The domes, built of wood and covered in sheet metal, are particularly vulnerable. The wood burns away and the metal shells collapse inward, falling into the inferno below. The square itself, cobblestoned for centuries, is heating to temperatures that would be painful to stand on, would eventually melt the mortar between the stones. In Beijing, the Forbidden City is living up to its name in a tragic way. Forbidden now not by imperial decree but by physics, uninhabitable and unapproachable. The ancient wooden buildings, built without nails in the traditional style, are burning with particular intensity. Wood, dry from centuries, ignites easily and burns hot. The red walls crack. The glazed tiles of the roofs fall and shatter. The treasures inside, art and artifacts from dynasties stretching back millennia, are being consumed. Sydney Opera House, that modern architectural marvel, is failing structurally. The concrete shells, heated unevenly by the intense radiation, develop stress fractures. The glass panels shatter from thermal shock. The harbour, normally a brilliant blue, is hidden beneath steam rising from its boiling surface. The Sydney Harbour Bridge, steel lattice spanning the water, is glowing red and sagging, no longer able to support its own weight as the steel loses strength. Rio de Janeiro's Christ the Redeemer statue, standing atop Corcovado Mountain with arms outstretched over the city, is cracking. The reinforced concrete, heated rapidly, expands at different rates in different parts of the structure. Cracks form, widening, until entire sections of the statue carve off and tumble down the mountainside. The statue's arms, those symbols of embrace and welcome, break and fall, leaving only a truncated torso that will itself eventually fail. In every city the pattern is the same. The buildings fail, the infrastructure collapses, the fires burn, and humanity, that species that built all these structures, that created civilization and art and music and literature, is gone. The people who walked these streets yesterday, who worried about mundane concerns like traffic and bills and relationships, are simply not present anymore. The cities have become monuments to absence, ruins in the making, archaeological sites for a future that will never come, because there will be no one to excavate them. The death toll is incomprehensible, not because the numbers are uncertain, eventually all 8 billion humans will be dead, but because the human mind cannot really process what 8 billion deaths means. We can imagine one death, our own or a loved one's, and feel the weight of that loss. We can perhaps imagine thousands of deaths, a tragedy we might read about in history books. But 8 billion? The number loses meaning, becomes abstract, just a statistic that conveys scope without emotional weight. Each of those 8 billion deaths is an individual tragedy. Each person had a name, a history, people who loved them, dreams for the future. Each person's death is the end of a unique perspective on the universe, a way of experiencing reality that will never exist again. The woman who was going to graduate next month, the child who just learned to ride a bicycle, the elderly man who was planning to see his grandchildren next week, the scientist who was close to a breakthrough, the artist who had just started a new work, all of them, gone. The deaths are not simultaneous. The radiation arrived everywhere on the day side at roughly the same time, but people die at different rates depending on their exact circumstances. Those directly exposed to the sun died first, within seconds. Those indoors or in shadow lasted perhaps a few minutes longer. Those with access to underground spaces might have survived an hour, but the ultimate result is the same. Whether death comes in seconds or hours, it comes for everyone, without exception, without mercy. The children die not understanding what is happening. The elderly die having lived long lives but denied the peaceful ends they might have hoped for. The young adults die with futures that will never unfold. Parents die unable to protect their children. Children die calling for parents who are already gone. Families die separated, some at work, some at school, some at home, never to be reunited. Friends die without goodbyes. Lovers die apart, their last words to each other mundane, not knowing they were final words. There are no heroic sacrifices, no last stands, no opportunities for courage or nobility. Death comes from the sky, impersonal and unstoppable, caring nothing for virtue or vice, age or youth, rich or poor. The dictator dies the same death as the saint. The murderer and the monk, the child and the elder, the genius and the fool, all experience the same end, brought by radiation that makes no moral judgments. In the hospitals, the sick die along with the doctors trying to treat them. The hospitals themselves, full of equipment designed to save lives, become death traps as power fails and backup systems overheat. Intensive care units, where the most fragile patients clung to life with the help of machines, go dark. Patients on ventilators suffocate. Those in surgery die on the table. The medical staff die at their posts, still wearing their scrubs, still trying to understand what is happening even as it kills them. In schools, children and teachers die together in classrooms. The children, depending on their age, have varying levels of understanding. The very young don't comprehend what is happening at all. The older children understand something is wrong, but not the scope. The teenagers might have enough knowledge to realize the sun has done something impossible, but not enough time to fully process that realization before death comes. In prisons, the inmates die locked in cells. The guards die at their posts. Neither group has any way to escape or seek shelter. The prison walls, designed to keep people in, succeed in this even as they fail to keep danger out. The distinction between prisoner and guard becomes meaningless in death. Both are simply people who happened to be in a particular place when the universe decided that place was no longer habitable. On highways and streets, vehicles crash as drivers are blinded or killed by the sudden light and heat. The crashes create pile-ups that block roads, not that the roads lead anywhere safe anymore. Cars become ovens, their metal bodies heating rapidly, their interiors uninhabitable within seconds. Those who try to flee their vehicles find the outside no better than the inside. Those who stay die where they sit, hands on steering wheels they will never turn again. At airports, planes on the ground are destroyed where they stand. Those in the air fall from the sky, as described earlier. The airports themselves, those liminal spaces of transition and travel, become monuments to journeys that will never be completed. Suitcases full of clothes and toiletries sit unclaimed, their owners dead, the destinations they were headed toward equally destroyed. In homes, families die together or separately depending on where each member happened to be when the pulse arrived. A father at work, a mother at home, children at school, all die apart, never knowing the fate of the others. In some homes, families were together, a weekend morning perhaps, everyone home for breakfast, and they die together. Small comfort in the face of annihilation, but something nonetheless. The pets, those animals humans kept for companionship, die confused and afraid. Dogs, cats, birds, fish in tanks all experience the same transformation of their environment from safe to lethal. They cannot understand what is happening. Their animal minds cannot construct an explanation for why the world has suddenly become hostile. They simply suffer and die, loyal to the end, waiting for humans who will never return to help them. In places of worship, people who sought comfort in religion die with prayers on their lips. Churches, mosques, synagogues, temples, all the structures humans built to connect with the divine, offer no protection from physics. The religious die the same deaths as the secular. Prayer does not shield against gamma rays. Faith does not reduce the heat. God, if God exists, watches the destruction of a planet with the same inscrutable distance with which God has always regarded human suffering. The last humans to die on the day side are those in the deepest, most insulated locations. Underground bunkers, deep basements, caves, anywhere that provides mass between the surface and the interior. These locations can't be reached by the radiation directly, but they heat through conduction. The rock and soil above them absorbs energy, and that energy conducts inward. It takes time, hours perhaps, but eventually the heat penetrates everywhere. The last survivors bake slowly in their refuges, their extended survival a curse rather than a blessing, giving them more time to fear and suffer before the inevitable end. On the night side, people have more time but not more hope. They can't see the sun, but they see the sky light up with auroras. They feel the winds beginning, the atmospheric storms generated by the heating on the dayside, they might understand that something has happened to the sun, might even guess that it has exploded, but they have no way to know that this grants them only hours rather than seconds. They have time to be afraid, time to say goodbyes, time to understand they are going to die. Whether this is better or worse than the instant deaths on the dayside is impossible to say. The cities stand empty now, or emptying rapidly. The silence is not peaceful. It is the silence of absence, of cessation, of an end to all the noise and bustle that defines urban life. No cars honking, no voices calling, no music playing, no footsteps on sidewalks, just the sound of buildings failing, of fires burning, of wind howling through streets that no longer have anyone to shelter. These cities, built over centuries or millennia, each with its own character and history, are being reduced to rubble in hours. All the human effort that went into constructing them, maintaining them, improving them, is being undone by energy from a star that cared nothing for human ambition. The cities are not being destroyed by war or deliberate malice. They are simply in a place that has become incompatible with their existence, and so they cease to exist methodically and thoroughly, leaving only heat and ruin and silence. The oceanic transformation. The oceans, covering 71% of Earth's surface, contain 97% of all water on the planet. This vast body of water, averaging 4 kilometers deep, has regulated Earth's climate and supported life for billions of years. Now, under bombardment from an exploded sun, these oceans are transforming into something alien, something that would be unrecognizable to any organism that evolved in their depths. The surface layer, the top few meters where light penetrates and where most marine life concentrates, is boiling vigorously. The energy from the radiation is being absorbed directly by the water molecules, heating them to temperatures far beyond normal. Water at Earth's surface, under normal atmospheric pressure, boils at 100 degrees Celsius. But the atmospheric pressure is no longer normal. It's dropping in some places, rising in others, fluctuating wildly as the air heats and convects. This changes the boiling point, sometimes lowering it, sometimes raising it, but the result is the same. Liquid water is rapidly transitioning to water vapor. The steam rising from the oceans is enormous in volume. A single cubic kilometre of ocean water, when converted to steam, expands to fill about 1 million cubic kilometres at normal temperature and pressure. But the steam being created is not at normal temperature. It's superheated, carrying even more energy than normal steam, expanding even more. This steam enters the atmosphere where it adds to the chaos already present. The water vapour, as it rises, encounters the chemical maelstrom of the altered atmosphere. Some of it is broken apart by photolysis, split into hydrogen and oxygen by the high-energy radiation still pouring in from the sun. The hydrogen, being the lightest element, rises to the upper atmosphere and begins to escape to space. Earth is losing its water, not all at once, but steadily, atom by atom, as the hydrogen that was once locked in H2O molecules achieves escape velocity and departs forever. The oxygen released by this photolysis does not escape. It is heavier, and Earth's gravity holds it. But this oxygen is not the stable O2 that makes up 20% of the normal atmosphere. It is atomic oxygen, highly reactive, looking for something to bond with. It finds plenty of options. Carbon dioxide, nitrogen oxides, sulfur compounds. All the chemicals churning through the atmosphere react with this free oxygen, creating new compounds that would never exist under normal conditions. Below the boiling surface layer, the ocean becomes stratified in unusual ways. The water density decreases with temperature, so hot water floats on cold water. This is normal. It's why the ocean surface is warmer than the depths in most places. But the current temperature gradient is extreme, with hundreds of degrees difference across a few meters. This prevents mixing. The surface water cannot sink even as it heats, because it remains less dense than the cooler water below. The result is a sharp thermocline, a boundary layer where temperature drops precipitously with depth. This stratification traps the heat near the surface. Under normal conditions, ocean currents mix warm surface water with deep water, distributing heat through the water column. The thermohaline circulation, driven by temperature and salinity differences, moves water through all the ocean basins over centuries, but now that circulation is disrupted. The surface water is too hot to sink, too light to mix, and the heat accumulates near the top. The marine life at the surface has already died. Fish, cetaceans, seabirds, anything that requires the surface layer has been cooked in the first minutes after the radiation arrived. The plankton, those microscopic organisms that form the base of the marine food web, are particularly vulnerable. Phytoplankton, the single-celled algae that perform photosynthesis, are killed instantly. Zooplankton, the tiny animals that eat the phytoplankton, die almost as quickly. With the base of the food web gone, everything that depends on it is doomed, even if it survives the immediate heat. In the deeper ocean, in the twilight zone where sunlight fades to nothing, organisms continue to exist for now. They don't see the sun, never have, and the heat has not yet penetrated to their depths. Squid and fish adapted to low light and high pressure hunt, and are hunted as they always have. They don't know that their world has ended at the surface. They don't know that no food will ever rain down from above again. They are living on borrowed time, destined to die eventually from starvation, if not from heat. In the deepest parts of the ocean, in the Hadal zone below 6,000 meters, where pressure exceeds 600 atmospheres and no light penetrates except for bioluminescence, life persists in the short term. These are some of the most alien environments on Earth, more hostile in their way than the surface of Mars, and yet life has found purchase even here. Strange fish with enormous mouths and tiny eyes, crustaceans that can survive pressures that would crush any surface organism, bacteria that feed on chemicals rather than light. All continue their ancient patterns of existence. For them, nothing has changed. The sun's explosion, the death of the surface world, the transformation of the atmosphere, none of it has reached them yet. They exist in a bubble of normalcy, deep in the abyss, unaware that they are the last living things on a planet that is dying from the outside in. They will be the last to perish, hours or days from now when the heat finally conducts down to their depths, or when they succumb to starvation in an ocean that has lost its productivity. The hydrothermal vents, those black smokers on the mid-ocean ridges where superheated water emerges from the seafloor, continue to function. These vents support their own ecosystems, independent of sunlight, based on chemosynthesis rather than photosynthesis. Giant tube worms, eyeless shrimp, specialized bacteria, all thrive around the vents in normal times. They might be expected to survive longer than other marine life, since they don't depend on the surface. But even these ecosystems are doomed. The vents themselves will continue to flow. They are driven by geothermal heat, by magma below the crust, processes that are not affected by what happens at the surface. But the organisms around them require more than just the chemicals from the vents. They need a specific temperature range. The vent water emerges at hundreds of degrees, but the organisms live in the gradient zone where this hot water mixes with cold ocean water. If the ocean water heats, if the temperature of the entire ocean rises beyond the organism's tolerance, they will die even at the vents that sustain them. The seafloor itself is beginning to experience changes. Sediments, accumulated over millions of years, layers of mud and sand and the shells of dead organisms, are being warmed from above. Normally the deep ocean floor is cold, just a few degrees above freezing. The sediments, compressed by depth and time, contain frozen methane in the form of methane clathrates or hydrates. These are ice-like structures where water molecules cage methane molecules, stable only at low temperature and high pressure. As the ocean warms, as heat slowly penetrates to the depths, these methane clathrates begin to destabilize. The methane released from its cage bubbles upward through the water column. Methane is a greenhouse gas, 25 times more potent than carbon dioxide at trapping heat. Under normal circumstances, a release of methane from the seafloor would be a climate concern, potentially driving warming. But now, with the surface of Earth already well past the point where climate matters, the methane's heat-trapping ability is irrelevant. It simply adds to the chemical complexity of the atmosphere when it reaches the surface, burning in the oxygen-rich air, creating more heat and more water vapor and more carbon dioxide. The coral reefs, those underwater cities of calcium carbonate built by tiny polyps over thousands of years, are dying in a particularly visible way. Corals are sensitive to temperature changes. Under normal warming, they bleach, expelling their symbiotic algae and turning white. If the temperature returns to normal quickly, they can recover. If not, they die and eventually crumble. Now, There is no slow bleaching process. The water temperature spikes far beyond anything corals have evolved to handle. The polyps die in their billions, their soft tissue disintegrating, leaving only the white skeleton. But even the skeleton doesn't remain intact. The calcium carbonate, under extreme heat, begins to undergo chemical changes. In water hot enough, it dissolves. The reef structures, built over millennia, begin to break down, returning to the ocean as dissolved calcium and carbonate ions. The Great Barrier Reef, visible from space in normal times as a band of turquoise water along Australia's coast, is dying along with everything else. The polyps that built it are dead. The fish that sheltered in it are dead. The ecosystem that depended on it, one of the most biodiverse places on Earth, has collapsed completely. The reef itself, that physical structure of limestone, is beginning to dissolve from the outside in. The ocean currents, those great rivers in the sea that move water around the globe, are being disrupted. The Gulf Stream, carrying warm water from the tropics to the North Atlantic, is being overwhelmed by even warmer water from the heated surface. The current circulation, normally driven by temperature and salinity differences, is breaking down as the temperature differences become too extreme and the patterns too chaotic. The Antarctic Circumpolar Current, the world's largest ocean current flowing around Antarctica, is being affected by the melting ice and changing temperatures. The current normally acts as a barrier, keeping cold Antarctic water separate from warmer water to the north. But with surface temperatures rising dramatically, this barrier is losing its definition. Water that should remain separate is mixing, creating eddies and instabilities in the current flow. The ocean's role as a carbon sink is ending. Normally, the ocean absorbs about a quarter of human carbon dioxide emissions, with the CO2 dissolving in seawater and eventually being used by marine organisms to build shells or simply remaining in solution. But warm water holds less dissolved gas than cold water. As the ocean heats, it releases carbon dioxide back to the atmosphere rather than absorbing it. Not that this matters now. The atmospheric CO2 concentration, normally a concern for climate change measured over decades, is irrelevant when the surface is already hot enough to melt rock. But it represents another reversal, another system that normally acts as a stabilizer for Earth's climate, being pushed into a regime where it does the opposite. The ocean's pH, normally slightly alkaline at around 8.1, is changing rapidly. The carbonic acid formed when CO2 dissolves in water normally lowers pH slowly, a process called ocean acidification that concerns marine biologists. But now, with CO2 being released from the warming water rather than absorbed, and with unusual chemistry happening throughout the water column, pH is fluctuating wildly in different regions. Some areas become more acidic as organic matter decomposes and releases acids. Other areas become more alkaline as minerals dissolve from sediments or as chemical reactions driven by the heat produce bases. There is no consistency, no global trend, just chaos as chemistry that normally takes place slowly and predictably instead happens rapidly and unpredictably. The bioluminescence, that eerie glow produced by many deep-sea organisms, continues in the depths where life persists. Jellyfish flash and glow. Lanternfish produce light from organs on their sides. Bacteria in the sediments emit a soft radiance. These lights, normally adaptations for hunting, mating, or camouflage in the eternal dark, now illuminate a world that is ending above them. The organisms producing the light don't know they are the last witnesses to Earth's ocean life, don't know that within hours or days their lights will wink out one by one as they succumb to heat or starvation. The icebergs, those floating mountains of ice that carve from glaciers and drift in polar waters, are melting rapidly. Not just the surface melting, which happens even under normal sunlight, but wholesale melting from the intense radiation and heated air and warmed water. Icebergs that might have existed for years, slowly drifting and eroding, are disappearing in hours. The water from their melting adds to the ocean. But the ocean is so vast that even thousands of icebergs melting simultaneously makes no measurable difference to sea level. Sea level itself is beginning to change, but not in the way one might expect. The water is heating and expanding. Thermal expansion would normally raise sea level. But simultaneously, water is being lost from the oceans through evaporation and photolysis faster than it can be replaced. The two effects partially cancel each other. In some regions, sea level rises slightly, in others, it falls. The coastlines, that sharp boundary between land and sea, are becoming fuzzy as steam obscures the transition and as the water level fluctuates. The beaches, those strips of sand between water and land, are transforming. The sand itself, silicon dioxide with various mineral impurities, is heating toward its glass transition temperature. In the hottest locations, exposed directly to the sun's radiation, the sand begins to fuse together, forming a glassy crust. This process, called vitrification, normally requires deliberate heat application or nuclear weapons. Now it is happening naturally across beaches worldwide. The tide, that regular rise and fall driven by the moon's gravity, continues. The moon doesn't know the sun has exploded. The moon experiences no radiation pulse because it happened to be on the far side of Earth from the sun when the pulse arrived. The moon continues in its orbit, pulling on Earth's water, creating bulges that manifest as high and low tides. This regularity, this continuation of a pattern that has existed for billions of years, is almost poignant in its irrelevance. The tide rises and falls on shores where nothing lives, where nothing will ever live again, maintaining its rhythm for an audience that no longer exists. The ocean floor, kilometers below the surface, sits in darkness as it always has. The pressure at those depths is so immense that water behaves strangely, its properties different from surface water. At the deepest point, the Mariana Trench's Challenger Deep, the pressure exceeds 1,000 atmospheres. Water there doesn't boil even at temperatures that would create steam at the surface. It remains liquid, dense and heavy, squeezed by the weight of the kilometers of water above. This deep water is the last reservoir of coolness on Earth. It will take days or weeks for the heat from the surface to conduct down to these depths. The water has thermal inertia, resisting temperature change because of its enormous volume and high heat capacity, but eventually, inevitably, the heat will penetrate even here. The ocean floor will warm, the deep water will heat, and the last cold place on Earth will cease to exist. When that happens, when even the deepest ocean has heated beyond habitability, Earth will have become completely sterile. Not just of complex life, not just of animals and plants, but of all life. Even the extremophile bacteria that survive in boiling springs and frozen wastes and radioactive environments will find no refuge. Temperature has limits even for extremophiles. Above certain thresholds, proteins denature, DNA breaks apart, cell membranes dissolve. Life, all life, has requirements that can be pushed but not broken, and Earth is being pushed far beyond those limits. The ocean will remain, at least for a while. The water won't all evaporate immediately. Earth's gravity is strong enough to hold much of it, even as hydrogen escapes to space. But it will be a dead ocean, lifeless and sterile, hot and toxic, nothing like the living waters that covered Earth for billions of years. It will be an ocean only in the sense that it is liquid water in a basin. Everything that made it an ocean, the life, the currents, the complex chemistry, the role in regulating climate will be gone. And beneath that ocean, in the sediments of the seafloor, lie the remains of countless organisms from Earth's history. Shells and bones, the hard parts that don't decompose, settling over millions of years to form layers of limestone and chalk. These fossil beds, records of ancient life, will be the last physical evidence that Earth was once inhabited. They will remain long after the surface has been scoured clean, long after the water has boiled away, long after any visitor to the solar system would have any reason to think this world ever hosted anything alive. But there will be no visitors. The sun has exploded, and with it, any chance that this system remains interesting to anyone. The planets, if they survive, will be sterile rocks orbiting nothing. There will be no reason for anyone to come here, no resources to extract, no mysteries to investigate, no beauty to appreciate. This ocean, Earth's ocean, will die unwatched and unmourned except by the organisms dying within it, and they do not mourn, they simply cease. The gravitational untethering. 8 minutes and 20 seconds after the sun exploded, Earth received the light, the radiation, the immediate catastrophe that killed the surface world. But light moves at the maximum speed causality allows, and other effects, while also moving at light speed, arrive at the same time. Gravity, despite feeling instantaneous, also propagates at light speed. The gravitational information about the sun's explosion arrives with the light. For 8 minutes after the Sun exploded, Earth continued in its orbit around a gravitational source that no longer existed. The planet was orbiting the Sun's past position, held in place by gravitational waves that left the Sun before it exploded. Earth was circling a ghost, a memory, following a path that seemed stable but was actually leading nowhere. Now that changes. The gravitational field that held Earth in orbit for 4.5 billion years suddenly ceases, or more accurately, suddenly weakens dramatically. The Sun, even after exploding, still has mass. Mass creates gravity, but that mass is no longer concentrated in a single 0.93 million miles away. It is being dispersed across the inner solar system as an expanding shell of plasma and debris. The gravitational effect of a sphere from the perspective of something outside it is the same as if all the sphere's mass were concentrated at its centre. This is why we can treat the Sun as a point mass when calculating orbits, even though it actually has a diameter of over 1 million kilometres. The distribution of mass doesn't matter as long as you're outside the distribution, but once the Sun explodes, once its mass spreads out into a shell, this simplification breaks down. Earth is now inside the shell of expanding solar debris, and inside a hollow sphere the gravitational effects cancel out. Pull from one direction is balanced by pull from the opposite direction. The net gravitational force inside a hollow sphere is zero, regardless of where inside the sphere you are. Earth's orbit begins to break. The planet continues moving in the direction it was travelling, roughly 30 kilometers per second tangent to its former orbital path. But without the Sun's gravity pulling it inward, providing the centripetal acceleration that kept it in orbit, the planet's path becomes a straight line. Earth is no longer orbiting. It is flying away into space on whatever vector it happened to have when the Sun's gravity ceased. This isn't immediately catastrophic. The immediate catastrophe was the radiation, which already killed everything. But gravitational untethering represents a longer-term doom, a guarantee that even if life somehow survived the initial pulse, even if some organisms endured in deep caves or sealed bunkers, they would eventually freeze and die as Earth left the inner solar system. The planet's trajectory carries it away from where the Sun used to be, out toward the asteroid belt and beyond. Earth is travelling at 30 kilometers per second, fast by human standards but slow on cosmic scales. At this speed, it would take thousands of years to reach even the nearest star. The planet will wander interstellar space, a rogue planet, carrying its cargo of sterilized water and rock through the void forever, or until it encounters another star system, which might happen in millions or billions of years, or might never happen at all. Space is vast and empty. Stars are separated by light years. A planet travelling at 30 kilometers per second might wander for the entire age of the universe without ever encountering another sun. The other planets are experiencing the same gravitational release. Mercury, closest to the Sun, receives the news first. Its tight orbit, taking only 88 days to complete, was held by strong gravity. When that gravity ceases, Mercury flies off on a trajectory that will take it somewhere, into the asteroid belt perhaps, or beyond. Its fate, like Earth's, is to wander until it either collides with something or drifts alone forever. Venus, Earth, Mars all become rogue planets simultaneously. The asteroid belt, that ring of debris between Mars and Jupiter, disperses. Each asteroid, each piece of rock that was orbiting the Sun continues on its own path. Some will collide with each other, some will be captured by Jupiter's gravity, some will escape the solar system entirely. Jupiter, massive and distant, feels the Sun's explosion less dramatically than the inner planets. Jupiter is so massive that its gravity dominates its region of space. The moons of Jupiter, Io, Europa, Ganymede, Callisto, orbit Jupiter, not the Sun directly. When the Sun's gravity ceases, these moons continue orbiting Jupiter as before. Their immediate situation doesn't change, but Jupiter itself, like the inner planets, is no longer bound to the Sun. The giant planet, with its mass of 300 Earths, begins to drift on its own trajectory. It takes with it its moons and its ring system, a complete miniature solar system travelling through space independent of any star. The Jovian system will remain intact, the moons still orbiting their planet, but the entire system is now nomadic. Saturn, Uranus, Neptune, the outer planets all experience the same liberation. They drift away from the solar system's centre, each on its own path determined by where it was in orbit when the Sun's gravity ceased. The solar system, that organised structure of planets circling a star, ceases to exist. What remains is a collection of wandering worlds, some alone, some with moons, all moving through space on independent trajectories. The comets, those icy bodies that normally reside in the distant Oort cloud and occasionally fall inward toward the Sun, are also affected. Those comets that were on their way inward, following elliptical orbits that would have brought them close to the Sun, suddenly find their trajectories changed. Without the Sun's gravity to pull them inward and then sling them back outward, they continue on whatever path they happen to have. Some will leave the solar system entirely, some will collide with planets, some will drift in the spaces between. Earth's moon, orbiting Earth rather than the Sun directly, continues its orbit unchanged in the short term. The moon doesn't care that the Sun exploded, it orbits Earth, held by Earth's gravity, and Earth's gravity hasn't changed. The moon continues to circle its planet, maintaining the same face toward Earth as it always has, pulling on Earth's oceans to create tides that no longer matter. But the moon is not immune to the effects of the Sun's explosion. The radiation pulse that sterilized Earth also illuminated the moon. The lunar surface, airless and unprotected, received the full intensity of the radiation. The rocks heated. The regolith, that layer of fine dust covering much of the surface, was sintered together in places by the heat. The ice at the lunar poles, water ice that has existed for billions of years in permanently shadowed craters, began to sublime, turning directly from solid to gas. The Apollo landing sites, those patches of lunar surface disturbed by human bootprints and machinery, have been altered by the radiation. The footprints, preserved for decades in airless vacuum, just remain. The radiation pulse doesn't disturb dust, but the equipment left behind, the flags and the retroreflectors and the descent stages of the lunar modules, have been heated and damaged. The American flags, already bleached white by decades of unfiltered sunlight, are scorched. The retroreflectors, used to measure the Earth-Moon distance by bouncing laser beams back to Earth, are misaligned by thermal expansion. Not that anyone from Earth will ever use them again. The humans who built them are dead. The telescopes that sent laser beams to them are destroyed. The moon continues to orbit a planet that has become a tomb, its surface marked by evidence of a species that briefly reached beyond their atmosphere and then died, leaving only artifacts that will erode over geological time until no trace remains. Earth's rotation continues. The planet spins on its axis, completing one rotation every 24 hours, unchanged by the Sun's explosion. The rotation is inertial, maintained by angular momentum, and nothing about the radiation or the loss of the Sun's gravity affects it. Day and night continue to alternate, although the meanings of day and night have changed. Day is no longer defined by sunlight. There is no sun. Night is no longer the absence of sunlight. Both are simply darkness, heated darkness on one hemisphere, cooling darkness on the other. The planet wobbles slightly as it rotates, a precession caused by the tidal effects of the moon and formerly the sun. Without the sun's tidal influence, this precession will change. Over thousands of years, Earth's axial tilt will evolve differently than it would have if the sun remained. The seasons, defined by this axial tilt, become meaningless. There are no seasons when there is no sun to provide varying amounts of light and heat. There is only the slow cooling of a world that has no external heat source. The internal heat of Earth, generated by radioactive decay in the planet's core and mantle, continues unchanged. This heat has kept the core molten for billions of years, and will continue to do so for billions more. It drives plate tectonics, powers volcanoes, and maintains Earth's magnetic field. None of this is affected by the sun's explosion, but without the sun, this internal heat becomes Earth's only heat source, and it is insufficient to keep the surface warm. Under normal conditions, the sun provides about 44,000 times more energy to Earth than the internal heat does. Losing that solar input means the surface will cool, will freeze, will eventually reach temperatures determined solely by the internal heat flux, which is minuscule. This cooling will take time. The surface, currently superheated by the radiation pulse, will remain hot for days or weeks. The oceans, heated but massive, will cool more slowly over months or years. The atmosphere will cool faster than the surface, over weeks. Eventually, over years, the surface temperature will drop to the point where water freezes, then to the point where carbon dioxide freezes, then to the point where nitrogen and oxygen begin to liquefy. Earth will become a dark, frozen world, orbiting nothing, wandering space with a thin layer of frozen atmosphere coating its surface. The oceans will freeze solid, kilometers of ice covering what was once liquid water. The atmosphere, having condensed and frozen, will form drifts of nitrogen and oxygen snow on the surface. The planet will be cold, dark, and completely dead, a relic of what it once was. This is the ultimate fate, years or decades in the future. But we're still in the hours immediately after the explosion, and Earth is still hot, still reeling from the radiation pulse, still processing the immediate catastrophe before the longer-term doom sets in. The gravitational untethering is not something anyone alive could perceive directly. There is no sensation of the orbit breaking, no feeling of release. If anyone were alive and conscious on the night side, they would not feel any different when the sun's gravity ceased. Earth's gravity holds them to the surface as it always has. The planet's motion through space feels no different whether it's orbiting a star or flying free. But instruments, if any survived the radiation pulse and the electromagnetic disruption, would begin to show anomalies. GPS satellites, their orbits calculated based on the gravitational influences of Earth, Moon, and Sun, would find their positions drifting from predictions. Radio telescopes observing pulsars for timing experiments would notice slight discrepancies as Earth's velocity vector changed. Calculations of planetary positions would begin to show errors. Not that anyone is alive to notice these discrepancies. The scientists who might have detected and understood them are dead. The instruments that might have measured them are destroyed. The computers that might have calculated them are offline. The gravitational untethering happens unobserved, another aspect of the catastrophe occurring to a world that has no witnesses, no one to understand or record what is happening. Earth flies alone into the dark, carrying 8 billion corpses and the ruins of a civilization that reached toward the stars but was destroyed by the star it depended on. The planet will continue, inert matter following the laws of physics, obeying gravity and momentum, but it will never again be home to anything living. Its story, the 4.5 billion year story of a living world, has ended. What remains is epilogue, the slow cooling and freezing of a corpse, taking thousands of years to complete but as inevitable as the heat death of the universe itself. The stellar debris arrives. Hours have passed since the radiation first struck Earth. The surface has been sterilized, the cities destroyed, the oceans boiled. But the radiation, devastating as it was, is only energy. The electromagnetic spectrum from gamma rays to radio waves, carrying enough energy to heat rock to melting but lacking any physical presence. Photons have no mass, no momentum beyond the minuscule radiation pressure. They can push solar sails, but they cannot physically displace objects of any significant size. What comes next is different. The sun, when it exploded, did not simply emit light. It expelled its matter. The star's outer layers, heated to millions of degrees by the shockwave from the core, were blown into space at thousands of kilometers per second. This matter, this actual physical substance that once made up our sun, has been travelling toward Earth since the explosion began. Light crosses the distance from sun to Earth in 8 minutes and 20 seconds. Matter, even very fast matter, takes longer. The leading edge of the stellar debris, moving at perhaps 1% the speed of light, 3,000 kilometers per second, takes roughly 15 hours to reach Earth's orbit. The slower material, the bulk of the sun's mass expelled at more modest velocities, will take days or weeks to arrive. Earth has had 15 hours since the radiation arrived. 15 hours of heat and destruction, of cooling corpses and burning ruins. The day side has rotated, putting former night into day and former day into night, though these terms mean little now. The planet has begun its journey into interstellar space, flying away from where the sun used to be at 30 kilometers per second. But Earth hasn't escaped the solar system's reach yet. The planet has travelled about 1.5 million kilometers in those 15 hours, less than 2% of the original distance to the sun. Earth is still well within the inner solar system, still in the path of the expanding debris cloud. The first particles to arrive are not what we would recognise as particles. They're individual atoms and ions, hydrogen and helium mostly, travelling at relativistic speeds. These particles have been accelerated by the explosion to a significant fraction of light speed. When they strike Earth's atmosphere, or what remains of it, they create particle showers similar to cosmic rays but far more intense. Each high-energy proton or alpha particle entering the atmosphere collides with air molecules, creating a cascade of secondary particles. These secondaries collide with more air molecules, creating tertiaries and so on, until the energy is dissipated across millions of particle interactions. The result is a spray of particles raining down through the atmosphere, adding to the radiation dose already received. Not that additional radiation matters to Earth's biosphere, everything is already dead. But the particle shower represents the arrival of the first physical matter from the Sun. The next phase of Earth's destruction is beginning. The density of these leading particles is low. They arrive scattered across space, individual atoms separated by thousands of kilometers. But they are traveling so fast that even individual impacts carry enormous energy. An atom of hydrogen moving at 10% light speed carries kinetic energy comparable to a rifle bullet, despite having a mass of only 1.7 times 10 to the minus 27 kilograms. As the hours progress, the density of incoming particles increases. More atoms arrive closer together, creating a more continuous stream. The upper atmosphere, already disrupted by the radiation pulse, is now being sandblasted by high-velocity atoms. The thermosphere, where satellites orbit, becomes a shooting gallery. Any satellites that survived the initial radiation pulse are now being destroyed by physical impacts. The International Space Station, its crew already dead from radiation, begins to disintegrate. The thin aluminum hull is punctured in thousands of places by hypervelocity impacts. Each impact creates a flash of light as kinetic energy converts to heat. The station, designed to withstand micrometeorite impacts, was never designed for bombardment on this scale. It begins to tumble as impacts destabilize its attitude control. Eventually it breaks apart, fragmenting into pieces that will eventually burn up in the atmosphere or be ejected into space. GPS satellites, communication satellites, spy satellites, the entire constellation of artificial objects in orbit around Earth are being methodically destroyed. The satellites can't maneuver to avoid the impacts. They lack fuel and their systems are dead anyway. They simply absorb impact after impact until their structures fail. Space, normally empty enough that satellites can operate for decades without being hit by anything significant, has become hostile to survival. On the ground, the particle impacts are absorbed by the atmosphere before reaching the surface. The air, even thinned and chemically altered, still provides some shielding. But the energy deposited in the atmosphere continues to heat it, maintaining temperatures far above normal. The atmospheric cooling that would normally begin after the radiation source was removed is delayed by the continued input of energy from particle impacts. The leading edge of the debris cloud is followed by denser material. The hydrogen and helium atoms, stripped of electrons and ionized by the heat of the explosion, arrive in increasing numbers. They form a plasma, a fourth state of matter that is neither solid, liquid, nor gas, but a soup of ions and free electrons. This plasma carries a magnetic field with it, the Sun's former magnetic field being dragged along by the moving charged particles. When this field reaches Earth, it interacts with Earth's own magnetic field in complex ways. The magnetosphere, already compressed by the intense solar wind in the hours after the explosion, is now being buffeted by magnetic fields embedded in the plasma. The interaction creates intense electrical currents in the magnetosphere and ionosphere. These currents, flowing through the plasma, create heat. The upper atmosphere glows with auroras far more intense than any before. The colours shift and swirl across the entire sky, visible from both dayside and nightside, though there is no one left to see them. The plasma, as it encounters Earth's magnetic field, is deflected around the planet. Earth's magnetosphere acts as a shield, diverting charged particles around it in two streams that rejoin beyond the planet to form the magnetotail. This protective effect is one reason life survived on Earth for billions of years. It prevents the normal solar wind from stripping away the atmosphere, but the flux of particles from the exploded Sun is far beyond what the magnetosphere evolved to handle. The magnetic field is overwhelmed. Particles that would normally be deflected instead punch through, following field lines down to the poles where they strike the atmosphere directly. The polar regions, already heated by the initial radiation, receive an additional dose of particle impacts. The aurora, normally confined to a ring around each pole, spreads toward the equator. The entire sky becomes a curtain of shifting light, green and red and blue, as oxygen and nitrogen atoms are excited by incoming particles and release photons as they relax back to ground states. This light show, beautiful under other circumstances, represents massive energy deposition into the atmosphere. Every photon emitted is energy that was brought by a particle from the sun and deposited into an air molecule. The atmosphere continues to heat, continues to churn, continues its transformation into something alien and hostile. Behind the leading plasma comes denser material, clumps of matter that were expelled from the sun's outer layers. These are no longer individual atoms, but collections of atoms still hot from the explosion, travelling somewhat slower than the leading edge but still moving at hundreds or thousands of kilometres per second. When these clumps reach Earth, they don't pass around the planet like the charged particles. They are electrically neutral, unaffected by magnetic fields. They follow ballistic trajectories, and if those trajectories intersect Earth, they impact. The first major impact occurs in the Pacific Ocean. A mass of solar material, perhaps 1,000 tons, strikes the ocean at 2,000 kilometers per second. The kinetic energy of the impact is enormous, equivalent to several nuclear weapons. The water at the impact point is instantly vaporized, along with some of the impacting material. The explosion sends a shockwave through the water and into the atmosphere. A plume of steam and plasma rises kilometers into the air. The shockwave in the ocean creates a wave, not a traditional tsunami, but a cavity that collapses behind the expanding bubble of vapor. The energy of this collapse creates secondary waves that propagate outward from the impact site. These waves are enormous, tens of meters high, carrying energy that would devastate coastlines under normal circumstances. But there are no coastlines anymore, not in the sense of places where land meets sea with clear boundaries. The coast is a zone of steam and fire, already destroyed by the radiation pulse. The waves, when they arrive, simply add mechanical energy to a zone that has already been thoroughly destroyed by heat. They lift and move debris, they erode structures that were already weakened, but they don't fundamentally change the state of destruction. More impacts follow. The solar debris is not uniformly distributed. It comes in clumps and streams with dense regions and sparse regions. Earth, flying through this expanding cloud, encounters impacts at random intervals. Some strike land, creating craters and explosions. Some strike ocean, creating steam plumes and waves. Each impact adds to the energy budget of the surface, keeping temperatures high, preventing any cooling. The larger impacts create effects beyond the immediate explosion. A particularly massive chunk, 10,000 tons of solar material, strikes in what used to be the Sahara Desert. The kinetic energy of the impact exceeds anything in human experience. The desert sand, already vitrified by the radiation pulse, is vaporized. The rock beneath is shattered and melted. A crater forms kilometers wide with walls of molten rock. The explosion launches material into the atmosphere and beyond. Some of the ejector achieves escape velocity, thrown so hard by the impact that it leaves Earth entirely. Other material falls back, raining down across a wide area as molten droplets that solidify into glass beads. The impact crater glows white hot, a new scar on a planet already scarred beyond recognition. These impacts continue for days as Earth plows through the expanding debris cloud. The frequency varies, with periods of intense bombardment followed by relative quiet, depending on the density of material in Earth's immediate vicinity. The total mass impacting Earth is small compared to the planet's mass, perhaps millions of tons, which sounds like a lot but is insignificant compared to Earth's 6 times 10 to the 24th kilogram mass. But each ton arrives with enormous kinetic energy, and that energy is deposited into Earth's surface and atmosphere. The cumulative effect is to keep the surface hot, to prevent cooling, to maintain conditions that are completely inhospitable to any form of life. If somehow an organism had survived the initial radiation pulse, the impacts would finish the job. The composition of the impacting material is interesting from a scientific perspective if there were any scientists left to study it. The debris represents a cross-section of the sun's layers. The earliest material to arrive comes from the outer layers, the photosphere and chromosphere, where temperatures were relatively cool and where heavier elements exist in small quantities. Later material comes from deeper in the sun, from regions where the temperature and pressure were higher and where helium is more abundant. The very last material to arrive, weeks or months from now, will include matter from near the Sun's core where fusion occurred. This material has a higher helium to hydrogen ratio than the outer layers. It may include trace amounts of elements heavier than helium, elements that were formed by fusion during the billions of years the Sun burned normally, or elements formed in the brief intense heat of the explosion itself. This material, falling onto Earth's surface, will mix with terrestrial matter. Silicon and iron and carbon from Earth's crust will blend with hydrogen and helium from the Sun. Future geologists, if there were any, might find these deposits and puzzle over their composition, wondering how solar material ended up concentrated in specific locations on Earth. But there will be no future geologists. Earth's story as a living world is over, and its future story as a dead world will be written in a language no one reads. The bombardment also affects the other planets and bodies in the inner solar system. Mercury, closest to where the Sun was, receives the densest and fastest moving material. The planet's surface, already vaporized by the initial radiation, is now being pounded by impacts that crater and reshape what remains. Venus, with its thick atmosphere, experiences a different kind of bombardment, with material impacting the upper atmosphere and creating friction heating that adds to the chaos below. Mars, farther out, receives less intense bombardment, but still experiences significant impacts. The thin Martian atmosphere provides little protection. The surface, already cold and dry and dead, is pockmarked with new craters as solar debris rains down. Any future human missions to Mars, planned for decades but never realized, would find a surface even more hostile than before, if such missions were possible from a species that no longer exists. The asteroid belt receives its share of impacts as well. Asteroids, already scarred by billions of years of collisions, add new craters from solar debris. Some asteroids are hit with enough force to change their trajectories, their orbits altered by the momentum transfer. The belt, already chaotic with countless individual orbits, becomes even more unpredictable as velocities and trajectories shift. Earth, after days or weeks of bombardment, eventually clears the densest part of the debris cloud. The planet has moved farther from the explosion site, and the material density decreases with distance. Impacts become less frequent, then rare, then cease entirely. The bombardment phase ends, leaving Earth battered but structurally intact, still a planet, still a coherent body, but thoroughly sterilized and fundamentally altered. The surface, seen from space if anyone were in space to see it, looks different. The familiar blue and white and green of the living Earth is gone. The planet is now brown and grey and black, with occasional glowing spots where recent impacts have created molten zones. The atmosphere is still present but altered in composition, thick with dust and vapour, obscuring the surface. The oceans are still there, or what's left of them, hidden beneath steam and clouds. Earth continues its journey into interstellar space, carrying the physical evidence of bombardment embedded in its crust. The solar material that impacted has become part of Earth. Atoms from the Sun mixing with atoms from the planet. A last embrace between star and planet. A mixing that would be beautiful if there were anyone to appreciate the poetry of atoms that once fused in the Sun's heart, now resting in Earth's crust. The bombardment has ended, but its effects remain. The craters, the altered surface composition, the heat deposited into the crust, all are lasting changes. Earth has been transformed not just by energy, but by matter, not just heated but physically reshaped. The planet that emerged from the debris cloud is not the same planet that entered it, even though the changes are small compared to the changes wrought by the initial radiation pulse. And still, Earth flies onward, away from where the Sun used to be, into the dark between stars, carrying its cargo of ruin into an uncertain future. The cooling begins. Days have passed since the Sun exploded. The radiation pulse sterilized the surface in minutes. The stellar debris bombarded the planet for days. Now finally, the immediate catastrophes have ended. What remains is the long, slow process of cooling, the gradual transition from a superheated world to a frozen one. The surface temperature, which peaked at over 1,000 degrees Celsius in some locations during the radiation pulse, has begun to drop. Without continued energy input from the Sun, the only heat sources are Earth's internal geothermal heat and the residual heat from the bombardment. These are insufficient to maintain surface temperatures anywhere near habitable levels. The atmosphere is the first to cool. Air has low thermal mass compared to rock or water, and it radiates heat efficiently into space. the temperature drops from hundreds of degrees to merely scorching, then to merely hot, then to something approaching what Earth's atmosphere used to be before the catastrophe. But the composition is wrong. The air is no longer the nitrogen-oxygen mixture that supported life for billions of years. It has been chemically altered by the high-energy radiation and the extreme temperatures. Nitrogen oxides formed during the heat pulse give the air a brownish tint. Water vapour, produced by boiling oceans, makes up a higher percentage than normal. Carbon dioxide, released from burning vegetation and heated rock, is more abundant. The weather patterns, driven by temperature differences, begin to reorganise themselves. The chaotic convection of the immediate aftermath gives way to more structured circulation. Hot air rises at the equator, cooler air sinks at the poles, and Coriolis forces create rotating patterns. These are not the same patterns Earth had before. The temperature distribution is different, the atmospheric composition is different, but they are patterns nonetheless, order emerging from chaos. Clouds form as water vapour cools and condenses. These clouds are thick and dark, covering large portions of the planet. They reflect what little light reaches Earth from the stars, though starlight is far too dim to warm the surface meaningfully. The clouds also trap heat radiating from the surface, slowing the cooling somewhat. Earth develops a greenhouse effect more intense than anything in its previous history. But it is not enough to prevent the ultimate freezing. Rain begins to fall in some regions, not the gentle rain of a normal spring, but torrential downpours as enormous amounts of water vapour precipitate out. This rain is acidic, carrying dissolved nitrogen and sulfur compounds from the altered atmosphere. It corrodes what remains of human structures, etching stone, dissolving metal, wearing away the last traces of civilization. The rain that falls on hot ground evaporates again, creating steam. But the ground is cooling, and eventually the rain persists long enough to create puddles, then streams, then rivers. Water flows downhill as it always has, obeying gravity, seeking the lowest points. The oceans, depleted by evaporation during the heat pulse, begin to refill slightly as rain accumulates and rivers carry it back to the sea. But the rain is not pure water. It carries dissolved minerals, salts leached from soil and rock, acids formed in the atmosphere. The oceans, already chemically altered by the heat and by photolysis, become even stranger. The salinity increases in some regions, decreases in others. The pH fluctuates. The ocean is no longer the familiar salty water that supported marine life, but a chemical soup, lifeless and hostile to anything organic. The ocean surface, which boiled during the heat pulse, has cooled enough that it is no longer producing steam. The water is still hot by Earth's previous standards, perhaps 60 or 70 degrees Celsius in places, but it is liquid water again, not vapour. The depth of the ocean has decreased somewhat. Water was lost to space via photolysis and evaporation, but the basins still hold enormous volumes of water. Beneath the surface in the deep ocean, conditions are closer to what they were before the catastrophe. The deep water was never heated as intensely as the surface. The pressure at depth kept it liquid even at temperatures that would boil surface water. The abyssal plains, kilometres below the surface, remain dark and cold and pressured as they always were. But even here, change is coming. The surface water, as it cools, will eventually become dense enough to sink. This will initiate a turnover, with surface water descending and deep water rising. This mixing will bring warm surface water to the depths and cool deep water to the surface. Over months or years, the entire ocean will equilibrate to a more uniform temperature. When this happens, the last refugees of slightly cooler water will vanish. The deep ocean organisms that survived the initial pulse because the heat didn't penetrate to their depths will finally encounter lethal temperatures, or they will already have died from starvation, because the surface productivity that normally reigns organic matter down to the depths has ceased entirely. Either way, the deep ocean's reprieve is temporary. The land surface cools more slowly than the atmosphere, but faster than the deep ocean. Rock has higher thermal mass than air, but lower than water. The crust, heated during the bombardment, radiates its heat away over weeks. The glowing hotspots, where impacts created molten zones, fade from white to orange to red to dark as they cool below incandescence. In volcanic regions, eruptions that began during the heat pulse continue for a while, then gradually cease. Volcanoes are driven by magma from the mantle, and the mantle was not significantly heated by events at the surface. The eruptions that occurred were triggered by stress in the crust from rapid heating. but that stress dissipates as the crust cools and stabilizes. The volcanoes return to dormancy, though the magma chambers beneath remain molten as they always were. The surface rock, once hot enough to melt in places, solidifies. In the deserts, where sand was vitrified into glass, the glassy surface remains, a permanent record of the heat that passed. In cities, where buildings melted, the ruins solidify into strange formations. Steel and concrete and glass mix together in ways no building was ever designed to have. The forests, burned during the heat pulse, are now fields of ash and charred trunks. The ash, light and dry, is picked up by wind and distributed across wide areas. Some of it settles in oceans, some in lakes, some on ice caps. Everywhere it falls, it leaves a layer marking this time in Earth's history. A thin dark band that future geologists would recognize as a catastrophe layer if there were future geologists. The ice caps, melted or partially melted during the heat, begin to refreeze as temperatures drop. The Arctic Ocean, which became open water, starts to develop ice again. Not sea ice at first, the water is still too warm, but glaciers on land where precipitation falls as snow rather than rain and accumulates in layers. Antarctica, covered in kilometers of ice before the catastrophe, lost much of its ice to melting and sublimation. The bedrock beneath, exposed for the first time in millions of years, is now visible. But as temperatures continue to drop, snow begins to fall on this bedrock again. Very slowly, over decades or centuries, a new ice sheet will form, burying the land once more. The atmosphere continues to cool, and as it cools, its capacity to hold water vapor decreases. More rain falls, more snow falls at higher latitudes and altitudes. The hydrological cycle, disrupted by the heat pulse, is re-establishing itself, though in a form quite different from before. The atmospheric pressure at the surface is changing as well. Some gases have been lost to space, hydrogen primarily, but also some helium and lighter molecules. Other gases have been sequestered, water vapor condensing to liquid, carbon dioxide dissolving in oceans. The total atmospheric mass has decreased somewhat, and the surface pressure is a bit lower than it was before the catastrophe. This lower pressure affects the boiling point of water, which decreases slightly. It also affects how sound travels through the air, though there is no one to hear any difference. The air, thinner and chemically altered, would sound different if anyone spoke into it, would carry sound differently, would smell different, would taste different, would feel different to breathe, if there were anyone to breathe it. The cooling progresses over weeks and months. Surface temperatures drop from scorching to warm to mild to cool to cold. The exact temperature at any given location depends on latitude, altitude, and local conditions, but the trend is the same everywhere, downward. Eventually, temperatures in polar regions drop below the freezing point of water. Lakes and rivers begin to ice over. The ground freezes, permafrost forming in regions where permafrost existed before the catastrophe, and in new regions as well. Ice crystals form in the soil, expanding and contracting with temperature cycles, weathering rock in ways that are indistinguishable from normal freeze-thaw weathering. As temperatures continue to drop, the freezing spreads toward the equator. Regions that were formerly temperate become Arctic. The oceans at high latitudes begin to freeze at the surface, forming pack ice that thickens over time. The frozen area expands, and the boundary between frozen and liquid ocean migrates toward the equator. This process takes years. Earth has enormous thermal mass, and cooling from hundreds of degrees to below freezing happens slowly. But it is inexorable. Without a sun to provide energy, without any external heat source, the planet must cool until it reaches equilibrium with the temperature of space and its own internal heat production. That equilibrium temperature is far below freezing. In the outer solar system, where sunlight is weak, moons and planets have surface temperatures of -100, -200 degrees Celsius. Earth, now wandering interstellar space, will eventually reach similar temperatures. As the decades pass, the oceans freeze solid. Not just the surface, but the entire depth. Ice forms at the surface and thickens downward. In the deep ocean, where pressure is high, the ice takes unusual forms, different crystal structures than normal ice, denser phases that form only under extreme pressure. Eventually, all of Earth's water is solid. The oceans are ice kilometers thick. The lakes are ice. The rivers are frozen solid. The water vapour in the atmosphere has condensed and frozen, falling as snow, leaving the air dry and thin. The atmosphere itself begins to freeze. Nitrogen and oxygen, which make up most of the air, liquefy at very low temperatures, nitrogen at negative 196 degrees Celsius, oxygen at negative 183. As Earth cools below these thresholds, the air begins to condense out, forming liquid pools on the surface. These pools freeze as temperatures drop further, creating deposits of solid nitrogen and oxygen. The atmosphere, which once extended hundreds of kilometers above the surface, becomes a thin layer of frost on the ground. The pressure drops to nearly zero. Earth becomes effectively airless, its atmosphere condensed and frozen, coating the surface in a layer of exotic ices. The planet is now a frozen, airless ball of ice and rock, wandering through space at 30 kilometers per second. The surface temperature is perhaps negative 200 degrees Celsius, cold enough that nothing remains liquid, cold enough that atmospheric gases are solid. The only warmth is deep underground, where radioactive decay in the core and mantle continues to produce heat, but this heat is buried under kilometers of frozen material and does not reach the surface. Earth has become a rogue planet, one of perhaps billions that wander the galaxy. It looks like the icy moons of the outer solar system, Europa, Enceladus, but larger. Its surface is white and grey and black, covered in different types of ice and frost and dust. From a distance, it would be hard to identify as a planet that once teemed with life. The only evidence of Earth's former life is buried under the ice. The fossils in rock layers, the ruins of cities, the altered atmospheric composition, the isotope ratios that suggest biological activity, all are preserved but hidden. An alien visitor, if one ever came to this frozen world, might drill through the ice and discover this evidence, might piece together that this dead planet was once alive, might wonder what happened to extinguish the life so thoroughly. But no visitors will come. Space is vast, and Earth is just one small planet among billions. The probability of anyone ever finding Earth again, ever recognizing what it was, ever caring about its story, is essentially zero. Earth will wander alone, frozen and dead, until the end of time or until it collides with something, whichever comes first. This is the final state, the end result of the sun's explosion. Not dramatic, not violent, just cold and silent and utterly devoid of anything that could be called life or activity. Earth has become a tomb, preserving in ice the remains of a biosphere that existed for billions of years and was extinguished in hours. The frozen monuments. Beneath kilometers of ice, the ruins of human civilization lie preserved. The cities, destroyed by heat and bombardment, are now encased in frozen water and solidified air. The buildings, or what remains of them, stand as monuments to a species that no longer exists, their forms distorted by damage but still recognizable as having been deliberately constructed. In what was once New York City, the bases of skyscrapers protrude through the ice. The upper floors collapse during the heat pulse, but the foundations, built deep into bedrock, remain. The steel and concrete, corroded by acid rain and weakened by heat, are now frozen solid, locked in place by ice that fills every crack and cavity. The subway tunnels, flooded when the rain came and then frozen, form a network of ice caves beneath the city. The trains, stopped on their tracks when the power failed, are encased in ice. The passengers, long since dead and decomposed as much as decomposition can happen, in extreme heat followed by extreme cold, are preserved as frozen remnants, tissue and bone locked in ice like prehistoric animals in glaciers. Central Park, burned during the heat pulse, is now under a sheet of ice. The trees are gone, burned to stumps and ash. The ponds, which boiled away, refilled with rain and froze, creating ice formations that fill the basins. The rocks, those glacial erratics that survived the heat, are now surrounded by ice again, as they were during Earth's last ice age, though the mechanism of their current burial is entirely different. The bridges, collapsed during the heat pulse, lie as twisted wreckage beneath the ice. The Brooklyn Bridge, its cables severed and its roadbed fallen, rests on the bed of the East River, now a frozen channel. The metal has corroded over the years of cooling, rust forming in the presence of water and oxygen before the freezing locked everything in place. Similar preservation has occurred in every city worldwide. London's buildings, Paris's monuments, Tokyo's skyscrapers, all are frozen ruins beneath ice. The Eiffel Tower collapsed into molten metal, solidified into a heap that is now covered by meters of ice. The pyramids of Giza, built to last millennia, remain standing, their stone largely intact but buried under ice that has obliterated the surrounding desert. The Great Wall of China, stretching thousands of kilometers, is mostly intact beneath the ice. Stone is more resistant to heat than steel or concrete, and the wall survived the heat pulse better than most structures. But it too is buried, invisible from the surface, just another geological feature in a frozen landscape. Rome's ruins, already ancient before the catastrophe, have become more ruined still. The Colosseum's stone walls, cracked by the heat, stand beneath ice. The Forum, once the heart of an empire, is a field of frozen rubble. The Vatican, burned during the heat pulse, is a pile of charred stone and twisted metal under the ice, its treasures destroyed, its archives lost. In the oceans, beneath the frozen water, the remnants of ships lie on the seafloor. The Titanic, which sank over a century before the sun exploded, rests where it always did, now under a roof of ice kilometers thick instead of water. Countless other ships, from ancient wooden vessels to modern container ships, dot the ocean floors, all preserved in the frozen water. The ocean floors themselves are archives of Earth's biological history. Sediments, laid down over millions of years, contain the shells of foraminifera and other microorganisms. These sediments, now frozen solid, preserve a record of past climates, past extinction events, past flourishing of life. The last layer, the layer formed during and after the sun's explosion, is anomalous, containing unusual chemistry and impact debris, marking the end of Earth's biosphere. In caves around the world, preserved evidence of early humans remains. Cave paintings, tens of thousands of years old, are still visible on cave walls, the pigments unchanged by the catastrophe that killed everything. The caves, insulated from the surface, did not experience the extreme heat. The art remains, silent testimony to a species that once created beauty, that once tried to make sense of their world through images. The fossilized remains of dinosaurs, buried for 66 million years since their extinction, remain where they were. The Capige boundary, the geological layer marking the asteroid impact that killed the dinosaurs, is still present in rock strata, a previous catastrophe preserved for no one to study. Above it, layers representing 66 million years of mammalian evolution, ending in the Anthropocene, the age when humans became a geological force, and above that the newest layer, the one representing the sun's explosion. This layer is thin, formed over just a few years, but distinctive. It contains impact debris from the stellar bombardment, anomalous isotope ratios from the radiation pulse, and a sudden absence of any biological markers. Future geologists, if any existed, would instantly recognize this layer as representing a catastrophe, though they might puzzle over its cause. The layer also represents a stratigraphic boundary, a point where everything changes. Below it, evidence of life is abundant. Above it, nothing. No fossils, no organic molecules, no isotopic signatures of biological activity. Just lifeless rock and ice, accumulating slowly as dust falls from space and as ice deposits form and sublimate in response to temperature cycles driven by orbital mechanics that no longer matter. Buried beneath this frozen surface are all the products of human civilization. Libraries, their books burned or frozen, containing knowledge that will never be read again. Museums, their collections destroyed or preserved in ice, artifacts from 100 cultures now equally dead. Laboratories, their experiments ended abruptly, questions left unanswered forever. The digital record stored on servers and hard drives and optical media has been destroyed. The electromagnetic pulse from the sun's explosion fried electronics. The heat melted storage media. The water from flooding and rain corroded circuits. Even if the storage media survived physically, there is no power to read them, no computers to run, no humans to interpret the data. All of human knowledge, accumulated over millennia, has been lost. The literature, the science, the art, the music, the philosophy, all existed only in physical media or in human brains, and both have been destroyed. The species that sent probes to other planets, that split the atom, that decoded DNA, has vanished completely. leaving only ruins that will erode over geological time until nothing recognizable remains. The irony is that some of the most durable human artifacts are the simplest. Stone monuments carved by ancient peoples survive better than modern steel and concrete structures. The megaliths at Stonehenge, built 4,000 years ago, remain standing beneath the ice, their stones intact. The moai of Easter Island, carved by Polynesian peoples, stand on their frozen island, their stone faces weathering slowly. These monuments will outlast almost everything else humanity built. They will stand for millions of years as the ice sublimates and reforms with climate cycles, as wind and water, when there is liquid water again, if ever, slowly erode them. They will be among the last evidence that an intelligent species once existed on this planet. Also durable are the space probes humanity sent to other planets. Voyager 1 and Voyager 2, launched in the 1970s, have left the solar system entirely. They carry golden records with images and sounds from Earth, intended as messages to any alien civilization that might find them. These probes will wander interstellar space for billions of years, long after Earth itself has been destroyed or transformed beyond recognition. The probes to Mars, rovers and landers scattered across the Martian surface, remain where they were, now buried under the debris from solar bombardment but otherwise intact. Mars, farther from the Sun, was less intensely affected by the explosion. The rovers will sit on Martian soil for millions of years until they are buried by dust or damaged by micrometeorite impacts, metal fossils of a species that briefly reached another world. The lunar landing sites, where humans walked on another celestial body for the first time, remain visible on the Moon's surface. The footprints preserved in airless vacuum are still there, though partially obscured by debris from the Sun's explosion. The flags, bleached by decades of solar radiation and then scorched by the explosion's heat, remain planted where astronauts put them. These lunar artifacts will last for millions or billions of years. The Moon has no atmosphere to weather them, no water to erode them. Only micrometeorite impacts will gradually erase them, a process taking geological spans of time. They are among the most permanent records of human existence, preserved on a dead world orbiting a dead planet. But all these artifacts, the ruins on Earth, the probes in space, the flags on the Moon, will eventually disappear. Stone erodes, metal corrodes, ice sublimates and reforms, grinding surfaces smooth. The universe tends toward entropy, toward the erasure of information, toward the maximum disorder permitted by the laws of physics. In a billion years, Earth will have been resurfaced by geological processes. Plate tectonics, driven by internal heat, will continue to operate. The continents will drift, collide, form new mountain ranges subduct into the mantle. The rocks containing fossils and ruins will be buried, melted, reformed into new rocks with no memory of what came before. In 10 billion years, if Earth survives that long, any star that captures the planet will eventually die itself. If Earth is captured by a red giant, it will be vaporized. If captured by a white dwarf, it will freeze even colder than it is now. If it remains rogue, wandering interstellar space, it will eventually suffer collisions or tidal disruption from passing stars that will break it apart into debris. The universe does not preserve individual stories. It operates on scales where planets are transient, where stars are brief, where even galaxies eventually disperse. The fact that one planet orbiting one star developed life and intelligence and civilization and then lost it all in a day is ultimately insignificant to the universe at large. But it was not insignificant to the beings who lived it. 8 billion humans experienced the end of their world, their fear, their pain, their confusion, their final thoughts were all real and immediate and overwhelming to them. The universe may not remember, but in the moment, it mattered more than anything else could matter. And now, they're gone. All of them, along with all the other life that shared their planet. The Earth continues, a lifeless ball of ice and rock, but the story of terrestrial life has ended. 4 billion years of evolution, from simple bacteria to complex ecosystems to intelligence and civilization, terminated in hours by an astronomical event that should never have happened. The frozen monuments stand beneath the ice, unseen and unseeable, preserving nothing for no one, slowly eroding toward oblivion in a universe that does not care and will not remember. The wandering dark. Earth drifts through space, unbound and alone. The velocity is 30 kilometers per second, the vector determined by where the planet happened to be in its orbit when the Sun's gravity ceased. This trajectory will carry Earth through the former solar system and eventually into interstellar space, the vast emptiness between stars. The journey out of the solar system takes time. Earth was 93 million miles from the Sun, 1 astronomical unit, a distance that light crosses in 8 minutes. At 30 kilometers per second, Earth covers 1 AU in about 57 days. The planet has been travelling for months now, since the immediate aftermath of the explosion, and has moved several AU from where the Sun used to be. Behind Earth, in the space it has already crossed, lies a debris field. The Sun's remains, the matter that was expelled during the explosion, has expanded into a vast cloud. This cloud is not uniform. It has structure, with denser clumps and sparser regions, all expanding outward from the explosion site at various velocities. The densest material, expelled at the lowest velocities, remains near where the Sun was. This material will eventually form a nebula, a glowing cloud of gas that might be visible from other star systems, though there are no stars close enough to see it with the naked eye. Over thousands of years, this nebula will cool and disperse, becoming indistinguishable from the general interstellar medium. The fastest material, accelerated to near light speed by the explosion, has already left the solar system entirely. These particles, racing outward at relativistic velocities, carry the news of the Sun's death to neighbouring stars. In 4 years, they will reach Alpha Centauri. In 8 years, Sirius. In 12 years, Tau Ceti. None of these stars have intelligent observers as far as we know, so the news arrives unnoticed. Earth's trajectory will eventually carry it past the orbit of Jupiter, if Jupiter remains in orbit, which it does not. Jupiter, like Earth, has been gravitationally untethered and is following its own path. The two planets might pass relatively close to each other, or they might never encounter each other again. Space is vast enough that even objects as large as planets can miss each other entirely. If Earth and Jupiter do pass close enough, Jupiter's gravity will affect Earth's trajectory. Jupiter is massive enough that its gravitational field extends over millions of kilometers. A close pass could alter Earth's velocity, slinging it in a different direction, increasing or decreasing its speed. But this is unlikely. The probability of a close encounter is low, and Earth will probably fly past Jupiter's former orbital region without ever coming near the giant planet. Beyond Jupiter's orbit lies the asteroid belt, or what remains of it. The asteroids, untethered like everything else, are dispersing. Each asteroid follows its own trajectory, and the belt is becoming a sparse, expanding cloud of rocks. Earth might encounter some asteroids on its outward journey, but space is so empty that even in the asteroid belt, collisions are rare. Past the asteroids lie the outer planets, Saturn, Uranus, Neptune. These giants, far from the Sun even when it existed, felt its warmth only weakly. They were always cold worlds, their temperatures dominated more by internal heat than by solar radiation. The Sun's explosion changed them less than it changed the inner planets, but they too have lost their gravitational anchor and are wandering on independent paths. Saturn's rings, those beautiful bands of ice particles, are beginning to disperse. The rings were held in place by Saturn's gravity and by the tidal forces from the Sun. Without the Sun's tidal influence, the ring dynamics change. Over thousands of years, the rings will spread out, becoming a sparse cloud around Saturn, and eventually the particles will either fall into Saturn or drift away entirely. Uranus and Neptune, those ice giants at the edge of the planetary system, are perhaps the least affected by the Sun's explosion. They were so far away that the radiation pulse, while still intense, was spread over a larger area and somewhat attenuated. Their surfaces, already frozen, experienced heating but not to the extreme levels the inner planets faced. They remain ice giants, though now wandering ice giants, unbound from the star they once circled. Beyond the outer planets lies the Kuiper Belt, a region of icy bodies including Pluto and countless other dwarf planets and comets. This region, extending from about 30 AU to 50 AU from the Sun, is also dispersing. The objects here were only loosely bound to the Sun to begin with, their orbital velocities low, their gravitational attachment tenuous. They are drifting away, each on its own path, transforming the Kuiper Belt from a belt into a diffuse cloud. Even farther out, at thousands of AU, lies the hypothetical Oort cloud, a spherical shell of comets surrounding the former solar system. These comets are so far from the Sun that they barely felt its gravity even when it existed. They are affected by the gravity of passing stars more than by the Sun. The Sun's explosion has changed their dynamics, but subtly. They continue to orbit the solar system's centre of mass, which no longer coincides with any object but is instead a point in empty space where the Sun used to be. Earth, flying outward at 30 kilometers per second, will take decades to cross the Kuiper Belt region. It will take thousands of years to reach the Oort cloud, and it will take tens of thousands of years to exit the Oort cloud entirely and enter true interstellar space, the region where the Sun's influence, even at its strongest, was negligible. During this journey, Earth remains frozen and dark. The surface temperature, determined by the balance between internal heat and radiation to space, is around -200 degrees Celsius. The planet radiates infrared radiation, thermal energy leaking away to space, but the internal heat production partially compensates, keeping the temperature from dropping to absolute zero. The planet's rotation continues. Earth still spins on its axis once every 24 hours, a rotation that has persisted for billions of years and will continue for billions more. Day and night still alternate, though these terms have lost their original meaning. There is no sun to define day. There is only darkness, slightly less dark on one hemisphere and slightly more dark on the other, a distinction without a difference. The Moon continues to orbit Earth. Luna, Earth's sole natural satellite, remains gravitationally bound. The Moon's orbit is stable, unchanged by the Sun's explosion. It circles Earth as it always has, taking 27 days to complete one orbit, maintaining tidal lock so that the same face always points toward Earth. The Moon is also frozen and dark. Its surface, briefly heated by the radiation pulse, has cooled back to its normal temperature of -150 degrees Celsius on the day side, -200 on the night side. But these distinctions are also meaningless now. There is no day side without a sun to define it. The Moon is uniformly cold, its temperature determined by internal heat and starlight, both negligible. The Earth-Moon system, bound together by mutual gravity, travels through space as a unit. They maintain their dance, orbiting each other, or more precisely, both orbiting their common centre of mass, which lies inside Earth due to Earth's greater mass. This binary system will remain bound for billions of years, long after both bodies have forgotten they were once warmed by a sun. As Earth travels outward, the stars do not change noticeably. The stars are so distant that Earth's motion, even over years, does not produce measurable parallax for most of them. The constellations remain the same. Orion, the Big Dipper, the Southern Cross, all the familiar patterns that humans named and told stories about, remain unchanged, but Earth's velocity, sustained over millennia, will eventually carry it far enough that the nearby stars begin to show parallax. Alpha Centauri, 4 light-years away, will appear to shift position relative to more distant stars as Earth's viewpoint changes. In thousands of years, if anyone were watching, they would see the constellations slowly deform, transforming from familiar patterns into new configurations. Earth is heading in a particular direction, determined by its velocity vector at the moment of gravitational release. This direction is somewhat arbitrary. It depends on where Earth happened to be in its orbit, but it will determine which region of the galaxy Earth explores. The planet might pass relatively close to a nearby star, or it might wander through empty space for millions of years without encountering anything. The probability of capturing by another star is low but not zero. If Earth passes close enough to a star within a few AU, the star's gravity could capture the planet, putting it into orbit. Earth would then have a new sun, though likely not a pleasant one. Most stars are red dwarfs, cooler and dimmer than the Sun was. Orbiting a red dwarf at a distance where temperatures allow liquid water would put Earth close enough that tidal forces would lock its rotation, giving it a permanent day side and night side. But capturing requires a precise trajectory and velocity. Most likely, Earth will pass by any stars it encounters at too great a distance or too high a velocity to be captured. The planet will simply swing past, its trajectory bent by the star's gravity, but not enough to prevent escape. Earth will continue on its way, deeper into interstellar space, a brief visitor to other stellar systems but never a resident. The journey through interstellar space will last for millions or billions of years. Space is incomprehensibly vast. The distance between stars is measured in light years, and Earth is travelling at 30 kilometres per second, which is only about 1/10,000th the speed of light. At this rate, reaching even the nearest star would take 40,000 years. During this journey, Earth will experience no warmth, no light, no change except the slow erosion of its surface by cosmic rays and micrometeorite impacts. The planet will be a frozen, dark, isolated sphere, carrying the story of a dead biosphere through a universe that never knew it existed. The universe itself will change on the timescales of Earth's journey. Stars will be born, will age, will die. Supernovae will explode, creating new heavy elements and seeding space with material for future planets. Galaxies will collide and merge, creating new structures. The universe expands, accelerating under the influence of dark energy, increasing the distance between galaxy clusters. Earth, wandering through this changing cosmos, remains fundamentally unchanged. It is a frozen body, geologically active in its interior but lifeless and static on its surface. It carries no observers to witness the wonders it passes. It records nothing. It simply exists, moving through space because motion is the natural state of objects and no force has stopped it. In a way, Earth has achieved a kind of immortality. The planet will exist for billions of years, perhaps trillions if it avoids catastrophic collisions. It will outlast the Sun, which would have died in 5 billion years anyway. It will outlast most stars currently in the sky, which will burn out and become white dwarfs or neutron stars or black holes. But this immortality is cold and empty. Earth persists not as a living world, but as a corpse, a relic, a monument to what once was. The fossils in its rocks, the ruins under its ice, the altered atmospheric composition frozen on its surface, all testify to a vibrant past, but they testify to no one. They are records for an audience that does not and will not exist. The wandering continues, endless and pointless, through a universe that does not care and will not remember. Earth, once the centre of everything to the beings who lived on it, has become nothing, just another cold rock among countless cold rocks, drifting through the eternal dark. The last lights. In the deep darkness, light persists in unexpected places. Not sunlight, the sun is gone, not starlight, the stars are too distant to provide meaningful illumination, but light from other sources, faint and fleeting, illuminates small corners of the frozen world. The first source is radioactivity. Deep in Earth's crust and mantle, radioactive isotopes continue to decay. Uranium-238, thorium-232, potassium-40, these unstable atoms break apart, releasing energy in the form of alpha particles, beta particles, and gamma rays. This decay happens continuously, has happened for billions of years, and will continue for billions more. The energy released is minuscule per atom, but Earth contains enormous quantities of radioactive material. The total heat output from radioactive decay is about 47 terawatts, roughly 3 times the total energy consumption of human civilization at its peak. This heat keeps the core molten, drives plate tectonics, and maintains the magnetic field. Some of this energy reaches the surface as heat, though the flux is small, about 87 milliwatts per square metre on average. This is far too little to warm the surface meaningfully, but it represents a tiny glow, infrared radiation from rocks that are warmer than they would be without radioactivity. In certain locations, this glow is more pronounced. Volcanic regions, where magma approaches the surface, emit more heat. Radioactive ore deposits containing concentrated uranium or thorium emit more radiation and more heat than surrounding rock. These hotspots, invisible to human eyes but detectable by infrared sensors if any existed, mark the places where Earth's internal energy comes closest to the frozen surface. The second source of light is cosmic rays. These high-energy particles, protons and atomic nuclei accelerated by supernovae and other violent events across the galaxy, constantly bombard Earth. When they strike the atmosphere, they create particle showers, cascades of secondary particles that rain down through the air. These particle interactions produce faint flashes of light, Cherenkov radiation, when particles move through the ice faster than light moves through ice. The flashes are brief and dim, but they occur constantly, billions per second across the planet's surface. The frozen world glows with these microscopic sparkles, a light show with no audience. The third source is phosphorescence from certain minerals. Some rocks, when exposed to radiation, store energy in their crystal lattices and release it slowly as visible light. This glow, called thermoluminescence when triggered by heat, or radioluminescence when triggered by radiation, persists for hours or days after the initial excitation. On Earth's frozen surface, rocks containing these minerals glow faintly. Uranium ore, in particular, can cause surrounding minerals to fluoresce, creating patches of dim green or blue light visible in the darkness. These glowing patches are scattered randomly across the surface wherever the right minerals happen to be exposed. The fourth source is the stars themselves. While individual stars provide negligible light, collectively they create a background illumination. On a moonless night on the old Earth, away from city lights, starlight was sufficient to see vague shapes. On frozen Earth, with no atmosphere to scatter light, and no moon phase to vary brightness, starlight provides constant dim illumination. The brightest stars, Sirius, Canopus, Alpha Centauri, shine with apparent magnitude -1 to -0.7. They cast faint shadows on the ice. The Milky Way, that band of concentrated starlight from our galaxy's disk, is brighter than from old Earth because there's no atmospheric scattering to wash it out. The frozen world exists under a sky more brilliant than any human ever saw, though there are no humans to see it. The fifth source is the aurora, though its character has changed. Without the sun's solar wind, the magnetosphere is no longer being constantly buffeted by charged particles. But cosmic rays still interact with Earth's magnetic field, and the field still funnels particles toward the poles. The result is a dim, persistent aurora, fainter than before but never absent. These auroras paint the polar skies in faint curtains of green and red, oxygen and nitrogen atoms excited by particle impacts and emitting photons as they relax. The curtains drift and shimmer, driven by fluctuations in the cosmic ray flux and by dynamics in Earth's magnetosphere. They are beautiful, though beauty requires an observer, and there are none. The sixth source is bioluminescence, though this is temporary. In the hours and days immediately after the sun's explosion, before the last organisms died, bioluminescent creatures glowed. Deep-sea fish with their photophores, jellyfish with their fluorescent proteins, bacteria in the sediments all produced light as they always had. But these lights are gone now. The organisms that produced them died, from heat or starvation, or the gradual cooling and freezing of their environment. The last bioluminescent glow from some bacterium in a deep-sea sediment, where conditions remained briefly hospitable, winked out days or weeks after the catastrophe. Now all biological light is extinct, along with the biology that produced it. The seventh source is the occasional meteor. Space is not completely empty. Dust particles and small rocks still exist, remnants of asteroids and comets that were dispersed when the sun exploded. When these particles strike Earth's atmosphere, or what remains of it, the thin frost layer on the surface, they create brief flashes of light from friction heating. These meteor impacts are rare but not absent, perhaps one per hour visible from any given location, more during periods when Earth passes through denser regions of debris. Each flash lasts a fraction of a second, a brief point of light in the darkness, then fades to nothing. The eighth source is internal to the ice itself. Under pressure, ice crystals can accumulate stress, and when they suddenly release that stress, they can produce light, a phenomenon called triboluminescence. This happens in glaciers on old Earth, creating brief sparkles when ice fractures under its own weight. On frozen Earth, as the ice sheet thickens and flows under gravity, as temperature cycles create expansion and contraction, the ice fractures and reforms constantly. Each fracture produces a tiny flash. The ice sheet, kilometers thick, glows internally with these sparks, a flickering luminescence visible if anyone could see through the ice, which no one can. The ninth source is gravitational potential energy being converted to light through tidal heating. The moon's gravity creates tides in Earth's ice sheet, raising and lowering the surface slightly. This flexing creates friction, which creates heat, which can excite atoms to emit photons. The effect is tiny but measurable in principle, adding a minuscule glow to Earth's heat budget. The 10th source, the most poignant, is the decay of radioactive isotopes in objects humans made. nuclear reactors, weapons, medical devices, research equipment, all contained radioactive materials. These materials continued to decay, producing heat and light. The reactors, now frozen and buried, still have fuel rods that glow, with Cherenkov radiation in the water that cooled them and then froze around them. Plutonium-238, used in radioisotope thermoelectric generators for spacecraft and remote equipment, continues to decay with a half-life of 88 years. Devices containing this isotope glow red-hot, melting the ice around them, creating small pockets of liquid water in the frozen world. These pockets are sterile. Any microorganisms that might have survived in them were killed by radiation, but they represent the last places on Earth where water is liquid. These 10 sources combine to create a dark world that is not completely dark, a frozen world that still has light, though the light is faint and sporadic and meaningless without observers. The photons are produced, travel through ice or air or vacuum, and are absorbed or scattered, carrying information that no one receives. If someone could stand on the surface of frozen Earth, protected somehow from the cold and airlessness, they would see a landscape lit by starlight, occasionally punctuated by meteor flashes. The ice would be white or blue or grey, depending on its composition and thickness. The sky would be black, with stars bright and untwinking in the absence of atmosphere. The auroras would shimmer at the poles, faint curtains of light in otherwise empty sky. The terrain would be varied. Impact craters from the stellar debris bombardment would create depressions in the ice. Mountains of rock would protrude through the ice in places where the ice is thinner. The ruins of cities would be invisible, buried under meters or kilometers of ice. But their foundations might create subtle variations in surface topography. The ice surface would not be smooth. Wind, during the period when atmosphere remained unfrozen, would have created drifts and patterns. Sublimation, the direct transition from solid to gas, would have etched the surface, creating rough textures. Cosmic ray impacts would have created tiny pits. The surface would be weathered and textured, a complex landscape of frozen water and frozen air and dust. In some regions, cryovolcanoes might occur. These are not volcanoes in the traditional sense, not eruptions of molten rock. Instead, they are eruptions of liquid water or slush from beneath the ice, driven by pressure or by localized heat sources. The liquid, upon reaching the surface and the near vacuum conditions there, would flash freeze or explosively decompress, creating fountains of ice crystals that settle back to the surface as snow. These cryovolcanoes would be rare and unpredictable, occurring only where conditions are exactly right. But they would reshape the local terrain, creating mounds and flows of fresh ice, covering old surfaces with new material. They would be the only geological activity on the surface, the only thing creating change in an otherwise static world. The ice itself would flow slowly under its own weight, like glaciers on old Earth but on a planetary scale. The thickness varies with latitude and topography, and this variation creates pressure gradients that drive flow. Ice from the poles, where it's thickest, flows toward the equator. Ice from high elevations flows toward low elevations. The flow is measured in centimeters per year. Glacially slow even by glacial standards, but it occurs. This flow buries things. The ruins of cities, already under ice, are pushed deeper as more ice accumulates above them. Artifacts on the surface are covered, preserved, transported. Over millions of years, objects initially at the surface could be carried hundreds of kilometers and buried kilometers deep, incorporated into the ice sheet's internal structure. The ice contains layers, like tree rings, recording conditions at the time each layer formed. The oldest layers, near the bottom, formed during the heat pulse and contain unusual chemistry. High concentrations of acids, anomalous isotopes, debris from impacts. The newer layers, formed from precipitation after the catastrophe, are purer, made of water that evaporated from the oceans and fell as snow. Reading these layers, if anyone could, would tell the story of Earth's transformation from living world to frozen corpse. The transition is sharp, occurring over just a few years in the ice record. Before, normal isotope ratios, normal chemistry, layers that would fit seamlessly into the longer record of Earth's ice ages. After, chaos, anomalies, a sudden shift that screams catastrophe to anyone trained to read ice cores. But no one will read these ice cores. The scientists who could interpret them are dead. Their equipment is destroyed or buried. The knowledge of how to read the record is lost. The ice preserves its story perfectly, but the story goes untold, held in crystal lattices that will eventually sublimate away, erasing the record atom by atom until nothing remains. The lights continue, faint and scattered across the frozen surface, illuminating nothing for no one, existing because physics demands they exist, not because anything is served by their existence. The photons are produced and absorbed in an endless cycle, carrying energy from one location to another, obeying Maxwell's equations and the laws of thermodynamics, indifferent to the absence of anyone who might appreciate or understand them. And in the darkness between the lights, in the shadows cast by starlight on ice, in the deep places where no photon has reached for years, the frozen ruins of civilization rest in silence, waiting for nothing, because nothing will come. The monuments stand, the fossils wait, the story is preserved, but preservation without transmission is just another form of loss. The last lights illuminate a world that has become its own tomb, beautiful and dead and utterly alone. The mathematics of ending. Numbers, unlike humans, survive extinction. The mathematical description of Earth's transformation continues to be true whether anyone exists to calculate it or not. The equations of thermodynamics, orbital mechanics, and radiative heat transfer describe frozen Earth exactly, predicting its future with certainty, even though no one will ever observe that future. The surface temperature can be calculated from first principles. Earth receives about 3.7 times 10 to the power of -6 watts per square meter from starlight, averaged over the entire surface. The planet also produces about 0.087 watts per square meter from internal radioactive decay. Together, these sources provide approximately 0.087 watts per square meter. Using the Stefan-Boltzmann law, which relates temperature to radiated power, we can calculate the equilibrium temperature. For a black body radiating 0.087 watts per square meter, the temperature is approximately 35 Kelvin, or -238 degrees Celsius. This is colder than anywhere on old Earth's surface, colder than Antarctica in winter, approaching the temperature of the coldest objects in the solar system. At this temperature, all familiar substances are frozen solid. Water, obviously, has been solid since temperatures dropped below 273 Kelvin. Carbon dioxide froze at around 194 Kelvin. Oxygen liquefied at 90 Kelvin and froze at 54 Kelvin. Nitrogen liquefied at 77 Kelvin and froze at 63 Kelvin. Earth's current surface temperature of 35 Kelvin means that even nitrogen and oxygen are solid. The atmosphere, once hundreds of kilometers thick, is now a layer of frost centimeters or meters deep, coating the ice in white crystals of frozen air. The only gases remaining in gaseous form are helium and hydrogen, and most of these have escaped to space due to their low molecular weight. The thermal conductivity of ice determines how fast heat from the interior reaches the surface. Ice conducts heat poorly, with a conductivity around 2 watts per meter, Kelvin. This means a layer of ice 1 kilometer thick creates a temperature gradient of about 43 degrees Kelvin from bottom to top for the geothermal heat flux of 87 milliwatts per square meter. Earth's ice layer, averaging perhaps 5 kilometers thick over the oceans and less over the continents, creates a significant insulating barrier. The base of the ice sheet, in contact with rock or liquid water, is warmer than the surface. Not warm, still well below freezing at surface pressure, but warmer. This creates a temperature profile through the ice, with the coldest temperatures at the surface and slightly warmer temperatures at depth. The ice flows under its own weight according to Glenn's flow law, an empirical relationship describing how ice deforms under stress. The flow rate depends on temperature and pressure, with warmer ice flowing faster than colder ice. The deep ice, under pressure from kilometers of overlying material and slightly warmed by geothermal heat, flows faster than surface ice. This differential flow creates internal stresses and can produce unusual ice structures. In glaciers on old Earth, ice can contain bands of recrystallized material, layers with different crystal orientations, zones of folding where flow was disrupted. Frozen Earth's ice sheet contains all these structures on a planetary scale, recording the complex dynamics of ice under pressure. The mass of Earth's ice sheet can be estimated. If the oceans, containing 1.4 times 10 to the 21st kilograms of water, are completely frozen, they form a layer averaging 3.7 kilometers thick over the ocean basins. Add ice from frozen atmosphere, perhaps 10 to the 18th kilograms, and ice from precipitation over the continents, and the total ice mass is approximately 1.4 times 10 to the 21st kilograms, roughly 0.02% of Earth's total mass. This seems small, but it represents a significant redistribution of mass toward the surface. The oceans, once liquid and conforming to sea level, are now solid and can pile up on land. Ice sheets over the continents add mass that wasn't there before. This redistribution affects Earth's moment of inertia, the distribution of mass relative to the rotation axis. The change in moment of inertia affects Earth's rotation rate. Conservation of angular momentum requires that if the moment of inertia increases, the rotation rate decreases. The effect is small, perhaps a fraction of a second change in the length of day, but it's real and calculable. Earth's rotation is slowing very slightly due to the redistribution of mass, though there are no clocks left to measure the change. Earth's orbit, or rather Earth's trajectory through space, can be calculated from the initial conditions. The planet left the solar system with velocity 30 kilometers per second at a specific angle determined by its orbital position when the Sun exploded. This trajectory can be propagated forward using Newton's laws of motion and accounting for the gravitational influence of any objects Earth encounters. The calculations show Earth will pass through the outer solar system over thousands of years, gradually increasing its distance from the Sun's former position. After about 40,000 years, Earth will be 1 light-year away, in the Oort cloud region. After 100,000 years, Earth will be 2 light-years away, beginning to approach the gravitational influence of other stars. The probability of capture by another star can be estimated using cross-sections and relative velocities. For a star to capture Earth, the planet must pass within the star's Hill radius at low enough velocity that it can't escape. The Hill radius depends on the star's mass and its distance from other stars. For a Sun-like star in the solar neighbourhood, it's roughly 1 AU. The density of stars in the Milky Way's disk is about 0.004 stars per cubic light-year. The time between close approaches to stars defined as passing within 10 AU is approximately 100 million years. The probability that any given close approach results in capture is less than 1%. Therefore, Earth might wander for billions of years before being captured, and might never be captured at all. More likely is a scenario where Earth passes close enough to a star to have its trajectory altered but not close enough to be captured. These gravitational assists, or rather gravitational encounters, will slowly change Earth's velocity and direction. Over millions of years, Earth's path through the galaxy will become a random walk, influenced by every star it passes, never settling into orbit around any of them. The thermal evolution of Earth's interior can be modelled using heat diffusion equations. The core, currently at about 5,000 Kelvin, is cooling as heat diffuses outward through the mantle. The cooling rate is slow, about 50 to 100 Kelvin per billion years, determined by the mantle's thermal conductivity and the rate of heat generation from radioactive decay. This cooling will eventually cause the core to solidify, starting with the inner core and working outward. When the outer core solidifies, Earth's magnetic field will cease, because the field is generated by convection of liquid iron in the outer core. Without the magnetic field, Earth will be more vulnerable to cosmic rays and solar wind from any star it approaches, though this hardly matters to a planet that's already frozen and dead. The radioactive decay providing Earth's internal heat follows exponential decay laws. Uranium-238 has a half-life of 4.5 billion years, meaning half of it has already decayed since Earth formed. In another 4.5 billion years, half of the remaining uranium will have decayed. The heat production from radioactive decay decreases exponentially, approaching zero but never quite reaching it. In 10 billion years, the heat production from radioactive decay will have decreased by a factor of about 5. Earth's interior will be significantly cooler, the core perhaps solidified, tectonic activity slowed or ceased. The planet will be geologically dead, or nearly so, though still rotating, still possessing mass and gravity, still obeying the laws of physics that require it to continue existing. The ice on Earth's surface will persist for billions of years, but not forever. Sublimation, the direct transition from solid to gas, occurs even at very low temperatures. The rate depends on vapor pressure, which decreases exponentially with decreasing temperature. At 35 Kelvin, water's vapor pressure is extremely low, about 10 to the power of negative 30 atmospheres, but it's not zero. At this vapor pressure, ice sublimates at a rate of approximately 10 to the power of negative 20 kilograms per square meter per second. This seems negligible, and on human timescales it is, but over billions of years it adds up. In 1 billion years, about 300 kilograms per square meter will sublimate, equivalent to a layer 300 meters thick. Earth's ice sheet, averaging a few kilometers thick, will therefore sublimate completely in about 10 billion years, give or take a few billion depending on local conditions. The water vapor produced will escape to space since Earth's gravity can't hold water vapor at these low temperatures. Earth will lose its oceans molecule by molecule over timescales comparable to the current age of the universe. The final state, after all ice is sublimated, will be a bare rock planet with no atmosphere and no oceans, similar to Mercury but colder. The surface will be rock and frozen minerals, any organic material long since decomposed or preserved in rock formations. The fossils will remain, those portions that mineralized before the heat pulse destroyed the organic material. They will be the last record of life, waiting in stone for an observer who will never come. The sun, had it not exploded, would have died in about 5 billion years, swelling into a red giant and engulfing the inner planets before shrinking to a white dwarf. Earth would have been vaporized in this process, completely destroyed. Instead, by exploding early, the sun granted Earth a different fate: frozen exile, wandering the galaxy for billions of years before eventually losing even its ice and becoming a cold, dry rock in the darkness. Is this fate better or worse than being vaporized by a red giant? The question is meaningless. Neither fate includes observers to experience it. But there's something haunting about the persistence of frozen Earth, carrying its cargo of ruins and fossils through space and time, preserving evidence of life for far longer than life existed, maintaining a record no one will read. The mathematics describes all of this with precision. The temperature, the decay rates, the sublimation, the orbital trajectory, all can be calculated and predicted. The equations don't care that everything is dead. They continue to apply, describing a physical system evolving according to natural laws, indifferent to the absence of anyone who might find the system interesting. Numbers survive extinction. The story of Earth's transformation, when told in equations rather than words, is complete and accurate and eternal, existing in the Platonic realm of mathematical truth whether or not anyone ever calculates it. The integral of Earth's cooling curve, the differential equations governing ice flow, the gravitational n-body problem describing Earth's path through the galaxy. All these mathematical objects exist necessarily, consequences of the logical structure of mathematics itself. In this sense, Earth's story continues forever, preserved not in ice or stone but in the abstract realm of mathematical truth, accessible to any mind capable of understanding differential equations and thermodynamics. Whether that mind exists in this universe or some other, in this time or some other, or indeed whether any mind exists at all. The mathematics endures, indifferent to the physical universe, describing what happened to one planet around one star with the same precision. It would describe any physical system, eternal and beautiful and completely uncaring. The absence. Absence, by definition, cannot be perceived. You cannot see what is not there, cannot hear silence except as the absence of sound, cannot touch emptiness. Yet absence has presence, a weight of its own, a shape defined by what surrounds it. Earth's absence from the living universe is palpable in ways that transcend the mere fact of death. Consider first the absence of sound. On living Earth, sound was everywhere. Birds sang at dawn, insects buzzed in summer, wind rustled leaves, rain pattered on roofs, oceans roared against shores, cities hummed with traffic and voices and machinery. Even in the quietest places, deep caves, remote deserts, the interior of soundproof rooms, there was sound at the molecular level, thermal vibrations, the movement of air. Now there is silence. True silence. On the frozen surface there is no atmosphere to carry sound. Vibrations cannot propagate through vacuum. If a meteor struck the surface creating an impact crater, the event would be silent from any distance away. The ice might crack and fracture, transmitting vibrations through solid matter, but these would not be sound in the usual sense. They would be seismic waves, felt rather than heard, if anyone existed to feel them. The absence of sound is total and permanent. There will never again be music on Earth, never voices raised in conversation or argument, never laughter or crying or singing. The last sound, whatever it was, a gasp of someone dying, the crack of a building collapsing, the hiss of steam, has faded into silence that will never be broken. Consider next the absence of light, or more precisely, the absence of the kind of light that mattered. There is still light as discussed, starlight, cosmic ray flashes, radioactive decay. But there is no daylight, no sunrise, no golden hour when light slants through atmosphere and illuminates the world with particular beauty. The cycle of light and dark that regulated life for billions of years has ended. Plants photosynthesized using sunlight, converting photons to chemical energy. Animals saw using reflected light. Eyes evolved over millions of years to detect specific wavelengths. Humans built civilizations around the daily cycle of light and dark, working in day and sleeping in night. All of this depended on the sun, and all of it is now absent. The absence is not just the loss of the sun itself, but the loss of everything the sun enabled. Warmth that made liquid water possible. Energy gradients that drove weather. Photosynthesis that formed the base of nearly every food web. The gravitational anchor that kept Earth in a stable orbit where life could evolve without dramatic temperature swings. All absent, and with them, the possibility of life. Consider the absence of motion in the sense of biological motion. Frozen Earth has motion, rotation, trajectory through space, internal convection in the mantle, flow of ice sheets. But these are mechanical motions, deterministic, predictable, lifeless. What's absent is the motion of living things, the unpredictable dart of a fish, the purposeful stride of a mammal, the graceful glide of a bird, the reaching growth of a plant toward light. Living motion has qualities that distinguish it from mechanical motion. It appears purposeful, even when purpose is an illusion created by evolution. It responds to stimuli in complex ways. It's inefficient in beautiful ways. Animals waste energy playing. Plants grow in twisted paths around obstacles. All of this motion, this animation, in the literal sense of being animated by life, is absent. The oceans, once full of swimming things from microscopic plankton to massive whales, are now solid ice. The air, once filled with flying insects and birds and seeds dispersed by wind, is frozen on the surface. The land, once crawling with arthropods and vertebrates and fungi and bacteria, is lifeless rock and ice. The motion has ceased entirely, and the cessation is permanent. Consider the absence of change in the biological sense. Frozen Earth changes, ice flows, craters form from impacts, radioactive isotopes decay. But these changes are purely physical, following physical laws. What's absent is biological change. Evolution, succession, growth, decay, reproduction, death in the biological sense. Evolution requires reproduction with variation and selection. Without living organisms to reproduce, evolution has ended. The 4 billion-year story of increasingly complex life, from bacteria to eukaryotes to multicellular organisms to intelligent beings, has terminated. The last evolutionary change was whatever mutation occurred in the last organism to reproduce before everything died. After that, nothing. Ecological succession, the process by which ecosystems change over time as species colonize and are replaced, has ended. The forests will never regrow after fire. The lakes will never refill with algae and fish. The coral reefs will never rebuild after damage. The process of ecological recovery, which operated for billions of years, allowing life to bounce back from catastrophes, cannot operate when there is no life left to recover. Individual growth has ended. No organism grows from seed to adult, from egg to butterfly, from child to elder. The last growth was the last cell division in the last living cell, and after that, nothing. Time passes but brings no development, no maturation, no aging in the biological sense. Decay in the biological sense, decomposition by bacteria and fungi, the recycling of organic matter, has ended. The corpses on Earth's surface did not decay normally. The heat sterilized them, destroying the bacteria that would have decomposed them. Then they froze, and bacterial decomposition cannot occur in frozen tissue. The bodies lie preserved in ice, mummified not by desert dryness but by polar cold, unchanging for millions of years until ice flow or sublimation eventually disperses their molecules. Consider the absence of complexity. Living systems are complex in specific ways that distinguish them from non-living systems. They maintain organization far from thermodynamic equilibrium, using energy to build and maintain structures that would spontaneously decay without energy input. They process information, storing it in DNA and using it to guide their responses to the environment. All of this complexity is gone. The organisms that were far from equilibrium are now dead and therefore at equilibrium with their environment. The information in DNA remains encoded in the molecular structure, but it's not being used. The genes are not being expressed. The proteins are not being made. The information is not guiding any process. It's like a library where all the books exist but no one reads them. The information is preserved but functionless. The ecosystems, those complex webs of interactions between organisms, have collapsed. Food webs with dozens or hundreds of species, each species interacting with others in complex ways, creating stability through redundancy and diversity, all gone. The network has been reduced to nodes with no connections, individual frozen corpses with no relationships to anything else. Consider the absence of experience. This is perhaps the deepest absence. Living organisms experience the world. Even bacteria respond to chemical gradients in ways that could be called a primitive form of experience. Plants respond to light, to gravity, to touch. Animals have nervous systems that create rich inner worlds of sensation and, in some cases, emotion and thought. Humans, with their complex brains, experienced the world in particularly rich ways. They saw colours and heard music. They felt pain and pleasure. They thought abstract thoughts and formed beliefs and created meaning. Each human mind was a unique perspective on reality, irreplaceable and individual. All of these inner worlds are now absent. The last experience was the last thought in the last dying brain. Perhaps a moment of confusion, perhaps terror, perhaps resignation. After that, nothing. No sensation, no thought, no experience of any kind. The universe continues, indifferent, but the perspectives on the universe, the ways of experiencing it, are gone. This absence of experience is total. There is no consciousness anywhere on Earth, no awareness of any kind. The photons strike the ice and are absorbed or reflected, but nothing sees them. The cosmic rays create particle showers, but nothing detects them except as unconscious physical interactions. Events occur, ice cracks, meteors impact, molecules sublimate, but nothing experiences these events. Consider the absence of the future, or more precisely, the absence of potential. Living Earth had potential. Species could evolve in new directions, ecosystems could recover from disturbances, humans could develop new technologies, create new art, make new discoveries. The future was open, filled with possibilities. Frozen Earth has no biological potential. The future is determined by physics. Ice will flow, impacts will occur, the planet will cool, but there is no openness, no possibility of surprise in the biological sense. Nothing new will evolve, no new species will appear. The story is over and the ending is known. Continued freezing until ice sublimates away over billions of years, leaving bare rock. This absence of potential is perhaps the saddest absence. Life is characterized by potentiality, by the possibility of change and growth and adaptation. Death is the end of potential. Earth has died not just in the sense that all organisms died, but in the sense that the planet has lost its potential for life, has become a place where life cannot return because the conditions for life cannot be re-established without a sun. Consider finally the absence of meaning in the human sense. Meaning is something humans create, patterns they impose on reality, significance they attribute to events. The sunrise was meaningful. It represented hope, new beginnings, the reliability of natural cycles. The seasons were meaningful, they structured the year, defined agriculture, inspired art and literature. All of this meaning is absent because the minds that created meaning are gone. The universe doesn't have inherent meaning. Meaning is something conscious beings create. Without conscious beings, events simply occur without significance. The ice flows, but it doesn't mean anything. The stars shine, but they don't represent anything. The planet wanders through space, but its journey has no purpose. This is perhaps the deepest absence, the absence of anyone to care that everything is absent. If a tree falls in a forest with no one to hear it, the question goes, does it make a sound? On frozen Earth, trees don't fall, they're already burned and frozen. But the question applies to everything. Without observers, without anyone to perceive or care or assign significance, events occur in a universe that doesn't notice them. Earth's absence from the community of living worlds is complete. The planet was once alive, teeming with organisms, processing energy, evolving, creating complexity. Now it's dead, frozen, inert, following purely physical laws without any biological component. The absence is total, permanent, and utterly indifferent to itself. And in this indifference lies perhaps the most profound absence, the absence of grief. Earth's death is a tragedy, but only to minds that can conceive of tragedy. The universe feels no loss. The stars don't mourn. The galaxies don't care. Life emerged on Earth, flourished for billions of years, developed intelligence and civilization, and then died, all without the universe noticing or caring. The absence of grief for Earth's death is perhaps the final absence, the one that makes all the others more absolute. The geological persistence. Earth's interior remains alive in ways the surface does not. Kilometers below the frozen crust, beyond the reach of the catastrophe that sterilized the surface, geological processes continue exactly as they did before the sun exploded. The mantle convects, driven by heat from radioactive decay and residual heat from Earth's formation. The core remains molten, its iron and nickel kept liquid by pressure and temperature that have nothing to do with the sun. Plate tectonics, that grand recycling system that has reshaped Earth's surface for billions of years, continues to operate. The lithosphere, Earth's rigid outer shell, is broken into plates that float on the more ductile asthenosphere below. These plates move at rates of centimeters per year, driven by convection currents in the mantle. Beneath the frozen oceans, the mid-ocean ridges continue to spread. Magma rises from the mantle, cools, and forms new oceanic crust. This crust moves away from the ridge, carried by the motion of the tectonic plates. Eventually it will reach a subduction zone where it will descend back into the mantle, completing the cycle. But the surface expression of this activity has changed. On living Earth, mid-ocean ridges were sites of hydrothermal activity, with hot water jetting from vents and supporting unique ecosystems. Now, the water is frozen. When magma rises at the ridge, it encounters not liquid ocean but solid ice. The heat melts the ice locally, creating pockets of liquid water that immediately refreeze when the heat source moves away. The melting and refreezing creates unusual structures in the ice, vertical channels where hot water rose and then froze, chambers where steam accumulated before condensing, mineral deposits precipitated from the hot water, now locked in ice. These structures, if anyone could see them, would tell the story of volcanism trying to continue in an ocean that no longer exists as liquid. Subduction zones continue to operate as well. Where oceanic plates meet continental plates or other oceanic plates, the denser plate descends into the mantle. This descent is driven by the plate's own weight. It's denser than the surrounding mantle, so it sinks. The sun's explosion did nothing to change the density of rocks, so subduction continues. As the descending plate reaches depths where temperature and pressure are high, it releases water that was trapped in minerals. This water rises into the overlying mantle wedge, lowering the melting point of the rock there and causing it to partially melt. The resulting magma is less dense than surrounding rock and rises toward the surface, creating volcanoes. On frozen Earth, these volcanic arcs continue to function. Volcanoes in the Andes, in Japan, in the Aleutian Islands, all the volcanic chains associated with subduction zones remain potentially active. Magma chambers exist beneath them, slowly filling with molten rock from below. Eventually pressure builds until eruption occurs. When eruption happens, magma rises through the crust and reaches the surface, but the surface is now frozen, buried under kilometers of ice. The magma melts through this ice, creating vertical shafts. Steam and volcanic gases vent through these shafts, releasing pressure. The lava, when it reaches the ice surface, spreads out, melting more ice, creating flows that eventually freeze solid when they cool. These eruptions create anomalies in the ice sheet, hotspots where the ice is thinner or absent, volcanic cones built of frozen lava rising above the general ice level, gas vents where volcanic emissions escape to the vacuum above. These features are scattered across the frozen surface, marking the locations where Earth's internal heat reaches the exterior. Continental collision continues as well, where two continental plates converge, and neither can subduct because both are too buoyant. Instead, they crumple, creating mountain ranges. The Himalayas, formed by the collision of India with Asia, continue to rise. The rate is slow, millimeters per year, but persistent. The mountains grow taller even though no one will ever climb them again. But the surface expression is different. On living Earth, the Himalayas were massive peaks of rock, with glaciers in the valleys and permanent snow on the higher summits. Now the entire range is buried under ice. The ice fills the valleys and covers the peaks, creating a smooth surface that obscures the rugged topography below. Only the tallest peaks might protrude through the ice as nunataks, islands of rock in a sea of frozen water. The collision also creates earthquakes as rocks fracture and slide past each other. These earthquakes shake the frozen surface, creating cracks in the ice. The cracks might be visible as dark lines in the otherwise white ice sheet, fractures that open and close as the ice shifts. Some cracks might be large enough to form crevasses, gaps in the ice that descend to unknown depths. Transform faults, where plates slide horizontally past each other, continue to operate. The San Andreas Fault in California, the Alpine Fault in New Zealand, the Dead Sea Transform, all these structures remain active. The rocks on either side of the fault move past each other at steady rates, storing elastic energy that is periodically released in earthquakes. These earthquakes generate seismic waves that travel through Earth's interior. The waves reflect and refract at boundaries between different materials, carrying information about Earth's internal structure. If there were seismometers to record them, these waves would show that Earth's interior is essentially unchanged from before the catastrophe. The same layers, crust, mantle, outer core, inner core, all remain in place with the same properties. Hotspots, where plumes of hot mantle material rise toward the surface, continue to function. The Hawaiian hotspot, the Yellowstone hotspot, the Iceland hotspot, all are driven by mantle dynamics that have nothing to do with the sun. These plumes rise through the mantle, partially melt near the surface, and create volcanoes. But the volcanoes they create now erupt beneath ice. The Hawaiian Islands, built by successive eruptions over the hotspot as the Pacific Plate moved across it, are now buried under frozen ocean. New eruptions add to the islands, but the lava cools in frozen water, creating pillow lavas and other structures typical of submarine eruptions, even though the water is now ice. Yellowstone, that massive volcanic system in Wyoming, remains active. The caldera, formed by a catastrophic eruption 640,000 years ago, sits atop a magma chamber that is slowly refilling. The next super eruption might occur in tens of thousands of years, or hundreds of thousands. The timing is unpredictable. When it happens, it will erupt through the ice sheet, creating a temporary lake of meltwater before the water refreezes. The eruption would be spectacular if anyone could see it. Lava fountains rising kilometers into the vacuum, ash clouds expanding in the thin or absent atmosphere, falling back to the surface in ballistic trajectories rather than being carried by winds. Lightning in the ash cloud as particles collide and create charge separation. All of this happening in near silence, without an atmosphere to carry sound, witnessed by no one. Earth's magnetic field persists, generated by the dynamo effect in the liquid outer core. Convection of molten iron, combined with Earth's rotation, creates electrical currents that generate the magnetic field. This field extends into space, creating the magnetosphere that shields the surface from charged particles. The field's strength and orientation fluctuate over time, as they always have. Every few 100,000 years the field reverses, with north and south magnetic poles swapping. These reversals are recorded in rocks as they form. Minerals containing iron align with the field at the time and preserve that alignment. The rocks being formed now, in the frozen crust and in lava flows from active volcanoes, record the current field orientation. The magnetic field matters less now than it did when Earth had life and atmosphere. It no longer protects a biosphere from radiation. It no longer prevents atmospheric stripping by solar wind. There is no solar wind without a sun, and little atmosphere to strip. But it persists, a remnant of the dynamic processes in Earth's core, continuing to operate because the physics that creates it remains unchanged. Isostasy, the balance between the buoyancy of the lithosphere and the weight of the material it supports, continues to operate. When mass is added to the surface, like an ice sheet, the lithosphere beneath it sinks into the more ductile asthenosphere. When mass is removed, the lithosphere rises. This process, called isostatic adjustment, occurs over thousands of years. On frozen Earth, the ice sheets represent significant added mass. The lithosphere beneath them is slowly sinking, depressing the surface. This depression creates basins that will persist even after the ice eventually sublimates away. Hudson Bay in Canada, the Baltic Sea, both are basins created by ice sheets during Earth's last glacial period. Frozen Earth is creating similar features on a global scale. When the ice eventually sublimates over billions of years, the lithosphere will slowly rise, a process that will take tens of thousands of years after the ice is gone. The surface will rebound, rising hundreds of meters in some locations. This rebound will create new topography, changing the elevation and shape of the continents in ways that will be the last major change to Earth's surface before the planet's geological death. Mantle plumes occasionally punch through the lithosphere in unexpected locations, creating large igneous provinces, vast fields of volcanic rock formed by massive eruptions. The Deccan Traps in India, the Siberian Traps in Russia, both formed from such events in Earth's past. Similar events might occur on frozen Earth, with eruptions that cover continental areas with lava, melting ice, creating temporary lakes, reshaping the surface. These eruptions would be the most dramatic events on frozen Earth, brief periods of intense activity in an otherwise static world. They would create new landforms, alter ice sheet thickness, change surface albedo. And then they would end. The magma would cool, the ice would refreeze, and the surface would return to its frozen stillness. Earth's interior will continue these geological processes for billions of years. The heat from radioactive decay will not run out in any time frame relevant to Earth's existence. The mantle will continue to convect, plates will continue to move, volcanoes will continue to erupt. Earth will remain geologically alive long after every trace of biological life has vanished. This persistence is both remarkable and meaningless. Remarkable because it demonstrates the power of geological processes, their independence from surface conditions, their continuation regardless of whether anyone observes them. Meaningless because geological processes, without life to interact with them, are just physics. Rocks moving, magma flowing, heat transferring, all following natural laws without purpose or significance. Yet there is something almost defiant about Earth's geological persistence. The surface is dead, frozen, sterile. But beneath, the planet churns and moves and reshapes itself, maintaining a kind of vitality that is not life, but is not entirely death either. Earth endures, not as a living world, but as an active planet, until even this activity eventually ceases billions of years hence, when radioactive decay can no longer power the convection that drives everything. The cosmic context. Earth's catastrophe, while absolute for everything that lived on it, is unremarkable in the broader context of the universe. Stars explode regularly, thousands of supernovae per second across the observable universe. Planets die regularly. Every star that dies takes its planets with it, sterilizing them or destroying them entirely. Earth's story is not unique, only personal to us because it was our story. In the Milky Way galaxy alone, there are an estimated 200 to 400 billion stars. If even a small fraction of these have planets, and observations suggest most stars do, then there are hundreds of billions of planets in our galaxy. Many of these planets have experienced catastrophes similar to Earth's, though through different mechanisms. Some were sterilized by supernovae of nearby stars, some were ejected from their systems by gravitational perturbations, some never developed life at all. The death of planets is not an aberration, but a fundamental aspect of cosmic evolution. Stars form from collapsing molecular clouds, burn for millions to trillions of years depending on their mass, and then die in various ways depending on their size. When they die, their planets go with them. This has happened countless times in the history of the universe and will happen countless times more. Earth's particular mechanism of death the sun exploding prematurely in a way it shouldn't, is impossible in reality, but the end result, a sterilized planet wandering space, is common. Many planets have been ejected from their systems through gravitational interactions with other planets or passing stars. These rogue planets, unbound from any star, drift through interstellar space just as Earth now does. Estimates suggest there may be billions of rogue planets in the Milky Way, possibly outnumbering planets that remain bound to stars. Some of these rogues were ejected during the formation of their planetary systems before life had time to develop. Others, like Earth in our thought experiment, were once inhabited but were sterilized by their ejection or by the death of their star. We cannot know if any of these rogue planets once hosted life. We have no way to detect them unless they happen to pass close to us or unless they gravitationally lens light from background stars. Even if we detected them, we couldn't determine whether they were once alive. The evidence would be buried beneath ice or eroded away by time. But statistical lie, if life is common in the universe, and we don't know whether it is, then some rogue planets probably were once inhabited. They would be wandering the galaxy, carrying frozen ruins and fossils, each one a memorial to a biosphere that flourished and then ended, witnessed by no one, remembered by nothing. Earth in our scenario has joined this population of cosmic orphans. The planet that developed life 4 billion years ago, that evolved complex ecosystems, that produced intelligence and civilization, is now indistinguishable from any other frozen rock wandering between stars. Its specialness is not recorded anywhere except in the structures of its ruins and the chemistry of its rocks. Information that will go unread. The universe is full of such endings. Every star that dies ends the story of any life that might have existed in its system. Main sequence stars like the Sun will swell into red giants, sterilizing their planets. Massive stars will explode as supernovae, obliterating everything nearby. Even small red dwarfs, which can burn for trillions of years, will eventually run out of fuel and fade to darkness, leaving their planets frozen. Some planets die more suddenly. A nearby gamma-ray burst, focused beam of radiation from a hypernova, could sterilize one side of a planet in seconds. A close pass by another star could eject planets from their orbits. A collision with a large asteroid or comet could extinguish all complex life, as happened to the dinosaurs on Earth 66 million years ago. Life, wherever it exists, is temporary. This is not pessimism, but physics. The conditions that allow life are narrow and unstable. They require liquid water, which requires specific temperature ranges. They require energy sources, typically from a star. They require chemical elements beyond hydrogen and helium, which had to be created in previous generations of stars. All of these conditions are temporary, maintained for finite periods before changing in ways that make life impossible. The typical lifespan of a biosphere, the time during which a planet can support life, is perhaps a few billion years. Earth's biosphere lasted 4 billion years before a hypothetical catastrophe. The Sun would have given Earth another billion years or so of habitability before increasing luminosity made it too hot. This is typical for planets around Sun-like stars. Red dwarf stars, smaller and cooler, might allow longer periods of habitability. Their planets could potentially remain in the habitable zone for tens of billions of years. But red dwarfs have issues too. They're prone to flares that could strip planetary atmospheres, and their habitable zones are so close that planets are likely to be tidally locked, creating unusual climate patterns. The point is that nowhere in the universe is life permanent. Every biosphere that ever existed or will exist is temporary, bounded by the formation of its planet on one end and the death of its star on the other end. The duration varies, but the pattern is universal. Life arises, flourishes, and ends. This universality provides context for Earth's catastrophe. What happened to Earth in our thought experiment, the sudden, premature end of a biosphere, is unusual in its mechanism but not in its result. All biospheres end eventually. Earth's ending, if it happened as described, would be faster and more violent than most, but the final state, a dead planet, is the fate of all planets eventually. Does this context make Earth's death less tragic? Not to humans, for whom Earth is unique, the only home we've ever known, the only life in the universe we're certain exists. But cosmically, Earth is one planet among billions, and Earth's biosphere is one among potentially millions or billions of biospheres, that have existed across the history of the universe does not privilege Earth. The laws of physics that govern Earth's star are the same laws that govern all stars. The chemistry that allowed life to arise on Earth is the same chemistry available anywhere with the right conditions. The evolution that produced complex life on Earth would produce complex life anywhere, given sufficient time and stable conditions. Earth is special to us, but not to the universe. This is both humbling and clarifying. Humbling because it places human importance in context. We are products of one planet, orbiting one star in one galaxy among billions of galaxies. Clarifying because it reveals that the pattern of existence we observe, life arising, evolving, ending, is likely universal, not unique to Earth. If we ever develop the technology to detect biospheres on other planets, we might find many. Current telescopes can detect the atmospheric composition of exoplanets, looking for biosignatures like oxygen and methane in combinations that suggest life. Future telescopes might directly image exoplanets and analyze their light for signs of vegetation or technology. If we find such biospheres, we would be observing them as they were when the light left them, years or centuries or millennia ago. Some of those biospheres might already be dead by the time we observe them, their stars having died or their planets having suffered catastrophes. We would be seeing ghosts, light from living worlds that no longer exist as living. This is the nature of astronomical observation at interstellar distances. The speed of light is fast but finite, and stars are far apart. We always observe the past, never the present. The Andromeda Galaxy, visible to the naked eye on dark nights, is seen as it was 2.5 million years ago. If Andromeda's entire biosphere, if it has one, died yesterday, we wouldn't know for 2.5 million years. In this sense, every observation of a distant living world is observation of a world that might already be dead. The light travels toward us, carrying information about life, while the source of that light might be experiencing catastrophe. The universe is full of such temporal mismatches, information about past states propagating through space, while the actual states change in ways we can't yet see. Earth, in our scenario, is now on the other side of this temporal mismatch. If any civilization within a few light years was observing Earth, they would still see it as a living world for years after the catastrophe. They would observe sunlight reflecting off blue oceans, detect oxygen in the atmosphere, perhaps even detect industrial pollution or artificial lights. They would have no idea that by the time they're making these observations, Earth is already dead. Eventually, years after the catastrophe, the light from Earth's death would reach these hypothetical observers. They would see the sudden change, atmospheric composition altered, temperature spiked, then cooled, surface frozen. They might deduce that something catastrophic happened to Earth's star. They might wonder if anyone survived. They might mourn, if they're capable of mourning, for a biosphere they never knew existed until they witnessed its death. But probably there are no such observers. Space is vast, stars are far apart, and technological civilizations, if they exist at all beyond Earth, are probably rare and scattered. Earth's death would likely go unobserved, unremarked, just another planet among billions undergoing the universal transition from living to dead. This lack of cosmic significance does not diminish the tragedy for those who experienced it. To the humans and animals who died, to the plants and bacteria that were sterilized, the universe's indifference is irrelevant. Their suffering and death were real and immediate, regardless of whether anyone elsewhere ever knows or cares. But it does provide perspective. Earth's story, unique and precious to us, is part of a larger pattern. The universe creates opportunities for life, planets in habitable zones around stable stars with the right chemistry and energy sources. Life arises by mechanisms we're still working to fully understand. It evolves, diversifies, becomes complex, and then it ends, when conditions change in ways that life cannot adapt to. This pattern has repeated countless times across the universe's history, and will repeat countless times more before the universe itself ends. Earth, in our scenario, has simply completed its cycle sooner and more suddenly than it otherwise would have. The pattern is fulfilled, the story complete, and the universe continues, indifferent and vast and full of other stories unfolding in the same way. The information that persists. Though all life is gone and all observers extinct, information about Earth's living past persists in multiple forms. This information is encoded in structures physical and chemical, waiting for no one, existing because the universe preserves patterns even when the processes that created them have ceased. The fossils, those mineralized remains of organisms, are the most obvious repository of information. Every fossil carries data about the organism it came from, its size, its shape, sometimes even details of its soft tissue or its behavior. The fossil record scattered through sedimentary rocks around the world is a library of Earth's biological history. On frozen Earth, these fossils remain exactly where they were. The rocks containing them are buried under ice now, but the ice protects them from weathering. In some ways, preservation is better than it was before. There is no water to dissolve minerals, no organisms to disturb the sediments. The fossils sit in darkness beneath the ice, unchanged, waiting for a geologist who will never come. The youngest fossils, from species alive when the sun exploded, will never be traditional fossils. Fossilization requires specific conditions: burial, mineralization, protection from scavengers and decay. The organisms that died in the catastrophe were not buried properly. They were cooked, frozen, and left on the surface or in the shallow layers of ice. Their soft tissues did not have time to mineralize before being destroyed by heat. But these organisms leave other traces. Their bones and shells, made of calcium phosphate and calcium carbonate, persist. These hard parts are scattered across Earth's frozen surface, buried in ice, preserving the shapes of dinosaurs that weren't actually dinosaurs. Earth's last dinosaurs died 66 million years ago, but mammals and birds and reptiles and fish, and all the creatures that lived in those final moments, these scattered remains, if someone could excavate them, would tell a specific story, a mass extinction event that killed everything simultaneously. The lack of selectivity, predators and prey dying together, young and old, large and small, all species at once, would indicate a global catastrophe rather than a normal extinction event where some species survive and radiate to fill empty niches. DNA persists as well, at least for now. The double helix, that elegant molecule encoding genetic information, is chemically stable under the right conditions. Frozen tissue preserves DNA better than hot or wet conditions. The corpses buried in Earth's ice contain cells, and those cells contain DNA, and that DNA can remain intact for thousands or millions of years if nothing disturbs it. Each genome is a historical document. It records mutations accumulated over evolutionary time, relationships between species, adaptations to specific environments. Human DNA contains sequences inherited from fish ancestors, from early mammals, from primate ancestors. The DNA of all organisms contains similar histories, layered information about evolutionary descent. On frozen Earth, billions of genomes are preserved in ice, each one a unique document. But they are documents in a language no one can read. The information is there, the sequences of nucleotides, the genes encoding proteins, the regulatory regions controlling gene expression. But without someone to sequence and interpret it, the information might as well not exist. Chemical signatures persist in rocks and ice. The isotope ratios of carbon, nitrogen, oxygen, and other elements in organic matter differ from those in inorganic matter because biological processes prefer certain isotopes over others. These ratios, preserved in rocks, indicate biological activity even when no fossils are present. The ice on Earth's surface contains these signatures. The water molecules themselves have isotope ratios determined by the temperatures at which they evaporated and precipitated. The dissolved chemicals have isotope ratios affected by biological activity in the oceans. An analyzing chemist, if one existed, could read these ratios like tree rings, reconstructing past climates and ecosystems from ice chemistry. Atmospheric composition, frozen onto the surface, carries information about the biosphere. Oxygen in the atmosphere was produced by photosynthesis. Without life continually producing it, atmospheric oxygen would react with rocks and be removed in geological time. The high oxygen concentration Earth had before the catastrophe is evidence of a productive biosphere. This oxygen is now frozen solid on the surface, along with nitrogen and trace gases. The ratios of gases, the presence of compounds like methane that are normally broken down by sunlight or reaction with oxygen, all carry information about the state of the atmosphere when it froze. A chemist could analyze this frozen air and deduce that Earth had a biosphere, could estimate its productivity, could perhaps even distinguish photosynthetic oxygen production from inorganic sources. The ruins of human civilization carry information of a different kind. The buildings, even destroyed and buried, have geometries that indicate intelligent design. The roads and bridges and tunnels form networks that suggest purposeful planning. The artifacts, tools, art, writing, technology carry obvious marks of intelligence, but this information is fragile. The ruins are being buried in ice, which will flow and grind them down over millions of years. Metal corrodes, stone weathers, plastic breaks apart. Within a few million years, most artifacts will be reduced to fragments, scattered and unrecognizable. Within tens of millions of years, even these fragments will be mostly gone, subducted into the mantle or ground to dust by ice flow. Some artifacts will persist longer. The golden records on the Voyager probes, now leaving the solar system entirely, are designed to last billions of years. The lunar landing sites, protected from weathering by the moon's airlessness, might remain recognizable for hundreds of millions of years. The geological layer representing human industrial activity, with its unusual concentrations of rare earth elements and synthetic compounds, will persist as long as the rocks containing it exist. But most of human civilization's information will be lost. The books, digital records, art, music, all the cultural products of humanity exist only in fragile media. Paper burns or rots. Hard drives fail. Even stone inscriptions erode. The Library of Alexandria burned and its contents were lost. Frozen Earth is a larger version of this loss, with all of human knowledge being erased over geological time. The mathematical and physical laws that humans discovered persist in a different sense. These laws are not dependent on humans having discovered them. They were true before humans existed and remain true after. The Pythagorean theorem, the laws of thermodynamics, the equations of general relativity, all are aspects of the universe's structure. They don't disappear when the mathematicians and physicists who formulated them die. But the formulations, the specific ways humans chose to express these truths, are lost. The notation, the language, the pedagogical frameworks, all the machinery humans built around mathematics and physics exist only in human artifacts and human brains. When the artifacts decay and the brain stop functioning, this particular way of understanding the universe vanishes, even though the underlying truths remain. An alien civilization discovering frozen Earth millions of years from now might deduce that intelligence once existed here. They might find the ruins, recognize them as artificial, infer that toolmakers built them. They might find fossils indicating complex life. They might analyze the frozen atmosphere and deduce a productive biosphere. But they couldn't reconstruct human culture. They couldn't read human languages. The Rosetta Stone might survive in some form, but without context it's just marks on rock. They couldn't understand human art or music or literature. They couldn't know what humans valued, what they feared, what they loved. All the specific content of human civilization would be lost, even if the fact of its existence remained detectable. This is the nature of information in the universe. Some information is robust, encoded in stable structures like fossils and chemical signatures. Some information is fragile, depending on specific media and conditions. And some information exists only in the patterns of thought in living minds, ceasing to exist when those minds cease. Earth's frozen surface and interior contain information about 4 billion years of biological evolution, ending in catastrophe. This information is more complete than any archaeological record humans ever compiled. Every organism that died is preserved somewhere, though most are buried too deep or scattered too widely to ever be found. It's the most thorough record of a biosphere imaginable. But it's a record no one will read. The information exists but is inaccessible, locked in ice and rock, described by physical laws that determine its preservation but not its meaning. Information without an interpreter is just structure, patterns in matter, no different from any other arrangement of atoms. In this sense, Earth carries its own obituary, written in fossils and chemistry and ruins. The story of what Earth was, how life arose and evolved and ended, is preserved with perfect fidelity. But obituaries are written for the living, not the dead. This one has no audience, will never have an audience, exists only because the universe preserves information whether or not anyone uses it. The information persists, but persistence without transmission is just another form of silence. The philosophical weight. The question, What if the sun exploded tomorrow is not primarily a scientific question. The science tells us it won't and can't happen. It's a philosophical question, an invitation to contemplate contingency, fragility, and the assumptions that underlie our sense of continuity and security. We live as if tomorrow will resemble today. We make plans, build structures, invest in futures we expect to inhabit. This is rational. The patterns we observe tend to continue, and planning based on continuity is more successful than planning based on randomness. But continuity is not guaranteed. It's a pattern we observe, not a law we can rely on. The thought experiment of the sun's explosion forces recognition that the continuity we assume could, in principle, be violated. Not by the sun's explosion specifically, that's impossible, but by any of numerous catastrophes that are physically possible. A nearby supernova, a gamma-ray burst, a large asteroid impact, even human-caused catastrophes like nuclear war or catastrophic climate change. These possibilities are not equally likely. Some are extremely unlikely on human timescales, but none are impossible, and all would disrupt the continuity we assume. This recognition creates a kind of existential vertigo. If the patterns we rely on could cease, what does that mean for the plans and structures built on those patterns? One response is to conclude that nothing matters if everything could end. This is nihilism in its strict sense, the belief that life has no inherent meaning or value. If everything could be destroyed at any moment, why do anything? Why build, create, love, if it can all be erased? But this response misunderstands the relationship between contingency and meaning. Meaning is not something inherent in the universe, waiting to be discovered. It's something created by conscious beings, attributed to experiences and relationships and goals. The fact that meaning is created rather than discovered, that it's contingent rather than eternal, doesn't diminish it. It's meaningful because we make it meaningful, and that remains true whether or not it persists forever. Another response is to embrace the contingency, to let awareness of impermanence heighten appreciation of what exists. This is closer to Buddhist philosophy, which sees impermanence not as nihilistic, but as a characteristic of existence that, once accepted, leads to reduced suffering and increased appreciation. If we know nothing lasts, we might cherish it more while it exists rather than taking it for granted. The sun will rise tomorrow, almost certainly. But the thought experiment asks, what if it didn't? What if all our assumptions about continuity were wrong? This question doesn't change the likelihood of the sun rising. That remains essentially certain, but it changes our relationship to that certainty, making it something to notice rather than assume. From another angle, the thought experiment highlights human insignificance. We are products of one planet orbiting one star in one galaxy. Our entire species has existed for a tiny fraction of cosmic time. Our civilizations are even younger. Everything we've built, everything we consider important, depends on conditions that are special and temporary. This insignificance is difficult to fully internalize. Our brains didn't evolve to think on cosmic scales. We're adapted to care about things at human scales, our families, our communities, our lifespans. Cosmically, none of this matters, in the sense that the universe doesn't care about human concerns and will continue regardless of what happens to us. But does cosmic insignificance imply meaninglessness? Only if meaning requires cosmic importance, which is not obvious. Meaning might be scale-dependent, valid at human scales even if not at cosmic scales. A parent's love for a child is meaningful at the human scale, regardless of whether the universe cares. The thought experiment also raises questions about what we owe the future. If humanity might end at any moment through catastrophe, should we focus on the present or invest in futures that might never arrive? This is not just philosophical. It affects decisions about resource allocation, environmental policy, long-term research. One view is that we should maximize present welfare, since the future is uncertain. Enjoy what we have now, rather than sacrificing for futures that might not exist. This has appeal but also problems. If everyone thought this way, civilization wouldn't have developed because civilization requires investment in future generations. The opposing view is that we should prioritize the long term, working to ensure human survival and flourishing across deep time. This requires sacrificing some present welfare for uncertain future benefit. But if the future is genuinely uncertain, If catastrophe could strike at any moment, these sacrifices might be wasted. The resolution probably involves balancing these perspectives rather than choosing one. We make reasonable investments in the future while also valuing the present. We work to reduce existential risks, asteroid deflection, nuclear non-proliferation, safe development of powerful technologies, while also ensuring current human welfare. The balance is judgment, not calculation, because we can't precisely quantify the probabilities or values involved. The thought experiment also illuminates the relationship between knowledge and comfort. Knowing that the sun could not actually explode tomorrow is comforting. It allows us to plan with confidence, to assume continuity, to avoid constant anxiety about cosmic catastrophe. Ignorance of impossible dangers is unnecessary, but knowledge of genuine dangers creates psychological burden. This is the paradox of existential risk awareness. The more we learn about genuine threats, climate change, pandemic risks, artificial intelligence risks, nuclear war, the more we recognize that catastrophe is possible even if unlikely. This knowledge is useful for mitigation but psychologically difficult. It's easier to live assuming everything will continue than to live with awareness that it might not. Psychologically healthy engagement with existential risk probably requires what psychologists call realistic optimism, acknowledging genuine risks while maintaining belief in our ability to address them. This is different from naive optimism, which ignores risks, and from pessimism, which sees risks as insurmountable. It's a middle path, informed but not paralyzed, aware but not despairing. The sun's hypothetical explosion, in this framework, serves as a thought experiment that makes existential risk concrete. It's easier to contemplate in abstract terms. Some catastrophe might end everything, than when it's made specific. The image of the sun exploding, of Earth frozen and wandering, makes the abstraction visceral. But the visceral quality comes with a cost. Too much contemplation of catastrophe can lead to paralysis or despair. The human mind wasn't designed to hold constant awareness of existential fragility. We're built to focus on immediate concerns, not cosmic threats. Forcing constant awareness of what could go wrong is psychologically unhealthy. The balance, perhaps, is periodic rather than constant awareness, occasionally contemplating our contingency and fragility, then returning to normal life with slightly altered perspective, using the awareness to adjust priorities, spending more time with loved ones, pursuing meaningful work, reducing existential risks, without letting it dominate consciousness. From yet another angle, the thought experiment raises questions about consciousness and its relationship to the universe. When all conscious beings on Earth die, does something fundamental change about reality itself? Or does the universe continue unchanged, with consciousness being merely an emergent property that arises and ceases without cosmic significance? Materialist philosophy suggests consciousness is a product of physical processes, neurons firing, chemicals interacting, and when those processes cease, consciousness simply ends without remainder. From this view, Earth's death in our scenario is the elimination of local pockets of consciousness, but the universe itself is unchanged. Matter continues to follow physical laws, unaffected by the absence of anything to experience it. But some philosophical traditions suggest consciousness has a more fundamental role. Idealism argues that consciousness is primary and matter is derivative. Certain interpretations of quantum mechanics suggest consciousness is required to collapse wave functions to make reality definite. From these views, the elimination of all consciousness on Earth might represent a more fundamental change than mere matter rearrangement. This is not a question science can answer, because science studies what can be measured and observed, and consciousness as subjective experience is not directly observable from outside. We can study neural correlates of consciousness, the physical processes that accompany conscious experience, but whether consciousness has existence independent of those processes is a metaphysical question beyond scientific methodology. What's clear is that with Earth's hypothetical death, the universe loses a particular kind of complexity, the self-reflective information processing that allows matter to understand itself. Humans are the universe becoming conscious of itself, as Carl Sagan noted. When humans die, the universe loses that self-awareness, at least locally, at least temporarily, unless consciousness exists elsewhere. This brings us back to the question of life in the universe. If Earth is the only place consciousness exists, its death would be cosmically significant, The universe's only way of knowing itself would cease. But if consciousness exists on millions of planets across the galaxy, Earth's death is just one local cessation among many. Sad for those experiencing it, but not cosmically unique. We don't know which scenario is true. The Fermi paradox, the apparent contradiction between high probability of alien life and lack of evidence for it, suggests either life is rare, or intelligence is rare, or technological civilizations are short-lived, or they exist but haven't contacted us. Each possibility has different implications for how we should think about Earth's value. If Earth hosts the only consciousness in a vast region of space, its preservation becomes extraordinarily important. If consciousness is common, Earth's uniqueness diminishes, though not its importance to those who live here. The thought experiment of the sun's explosion highlights this uncertainty. We're contemplating the death of possibly the only conscious beings in light years, or possibly just one among many. The philosophical weight of the question, then, comes from multiple directions. It forces recognition of contingency and impermanence. It highlights human insignificance and significance simultaneously. Insignificant cosmically, but significant as potentially rare sites of consciousness. It raises questions about meaning, about what we owe the future, about how to live with awareness of fragility. These are not comfortable questions. They don't have clean answers. They sit in the realm of philosophy rather than science precisely because they involve values and meanings and subjective experience, things that can't be measured or calculated. But they're questions worth contemplating because they affect how we understand our existence and how we choose to live. The sun will almost certainly rise tomorrow. But the thought experiment asks, what does it mean that we exist in a universe where it could, in principle, not rise? What does our dependence on cosmic conditions tell us about our place in reality? How should we live with awareness that everything depends on patterns that could theoretically cease? The answers are individual and varied. Some find comfort in religious frameworks that place human existence in a larger cosmic narrative with ultimate meaning and purpose. Some find meaning in the temporary nature of existence, in the preciousness of what exists precisely because it won't exist forever. Some focus on legacy, on contributing to projects that will outlast them. Some simply live in the present, finding meaning in immediate experience without worrying about cosmic context. All of these are valid responses to the philosophical weight of contingency and impermanence. The thought experiment doesn't dictate any particular response. It simply makes explicit what's usually implicit, that we exist on a small planet orbiting an ordinary star in a vast universe, that our existence depends on conditions that are special and temporary, that everything we value could end, though almost certainly won't end in the specific way the thought experiment imagines. What we do with this awareness is up to us. We can ignore it, which is what most people do most of the time, and this is probably healthy. We can occasionally contemplate it, letting it adjust our perspective and priorities. We can build our lives and philosophies around it, making impermanence central to how we understand existence. Each path has merits and drawbacks. The philosophical weight, ultimately, is the weight of being conscious in a universe that doesn't require consciousness, of being alive on a planet that could have remained lifeless, of existing at all when non-existence is the default state and the eventual state of everything. This weight is bearable, even if occasionally heavy, and the thought experiment of the sun's explosion is just one way of making it explicit, one prompt to think about what existence means when it's contingent rather than necessary, temporary rather than eternal, precious precisely because it's fragile. The alternative endings. The sun exploding tomorrow is impossible, but Earth has many possible actual endings, each with different timelines and mechanisms. Understanding these alternatives provides context for the thought experiment and highlights what makes the imagined scenario unique or typical. The most certain ending is the sun's death in approximately 5 billion years. This is not an explosion, but an expansion. The sun will exhaust its hydrogen fuel and begin fusing helium in its core. This process makes the star swell, becoming a red giant with a radius extending to Earth's current orbit or beyond. Earth will be engulfed by the expanding sun and vaporized, but Earth's habitability will end long before vaporization. As the sun ages, its luminosity gradually increases. It's already about 30% brighter than when life first appeared on Earth. In approximately 1 billion years, perhaps less, the the sun will be bright enough that Earth's oceans will evaporate. The planet will experience a runaway greenhouse effect similar to Venus, with surface temperatures reaching hundreds of degrees. This warming will sterilize Earth's surface, but perhaps not its deep subsurface. Bacteria living kilometers underground, away from surface heat, might survive longer. But eventually, even these deep organisms will die as heat penetrates the crust. Earth's biosphere will end not in a moment, as in our thought experiment, but over millions of years, with life retreating to deeper refuges before finally being extinguished. This is Earth's most likely ending if nothing else intervenes. It's slow, predictable, and unavoidable without technological intervention. Humanity, if it still exists in 1 billion years, would need to have either left Earth for other worlds, or developed technology to move Earth's orbit farther from the Sun, or to shield it from increased solar radiation. A faster ending could come from asteroid impact. The asteroid that killed the dinosaurs was about 10 kilometers in diameter and released energy equivalent to billions of nuclear weapons. It didn't sterilize Earth completely. Many organisms survived and life recovered, but a larger impact could be more devastating. An asteroid 100 kilometers in diameter, if one struck Earth, would release enough energy to vaporize the oceans and melt the crust. The impact would create a brief atmosphere of rock vapor, temperatures of thousands of degrees, and would effectively sterilize the planet. This is comparable in destructiveness to our sun explosion scenario, though the mechanism is different. Such impacts are extremely rare. The asteroids large enough to cause this level of damage are known and tracked, and none are on collision courses with Earth. The probability of an unknown asteroid of this size hitting Earth in the next million years is very low. But over billions of years, the probability increases. Eventually, if nothing else ends Earth first, a catastrophic impact might occur. A supernova in Earth's neighborhood could sterilize the planet from a distance. If a massive star within a few dozen light years exploded, the gamma radiation could strip Earth's ozone layer and deliver a lethal dose of radiation to the surface. This wouldn't vaporize Earth or dramatically heat it, but it would kill surface life through radiation damage. The nearest star capable of becoming a supernova is IK Pegasi, about 150 light-years away, far enough that its eventual supernova won't affect Earth significantly. Betelgeuse, a red supergiant that might explode any time in the next 100,000 years, is about 600 light-years away, also safe. So supernova sterilization, while possible in principle, is unlikely to be Earth's actual ending. A gamma-ray burst, even more powerful than a supernova, could sterilize Earth from thousands of light-years away if the beam happened to point at us. These bursts, from hypernovae or colliding neutron stars, create focused beams of radiation that can deliver lethal doses across vast distances, but they're rare and randomly directed. The probability of Earth being hit by one is very low over the Sun's remaining lifetime. Human-caused endings are possible on shorter timescales. Nuclear war could render Earth uninhabitable through direct destruction, radioactive fallout and nuclear winter, cooling caused by smoke-blocking sunlight. This wouldn't sterilize Earth completely. Some organisms would survive underground or in oceans, but it could end human civilization and cause a mass extinction. Catastrophic climate change could make Earth largely uninhabitable for humans and many other species, though it's unlikely to sterilize the planet completely. Even the worst-case warming scenarios leave some regions habitable, and most organisms capable of surviving somewhere. Climate change is more likely to cause a reorganization of the biosphere than a complete end. Engineered pandemics or runaway nanotechnology could, in principle, sterilize Earth if they were designed to target all life rather than just humans. A self-replicating system that consumed biomass faster than organisms could reproduce would eventually consume the biosphere. This is wildly speculative and probably impossible, but it represents a theoretical human-caused sterilization scenario. Artificial intelligence, if it became super-intelligent and misaligned with human values, could end human civilization and potentially biological life if it decided to convert Earth's biosphere into something else. Computers, factories, whatever infrastructure it valued. This would be fast, measured in years or decades rather than millions of years, more like our thought experiment's timeline than the Sun's natural death. Each of these endings has different characteristics. Some are fast, some slow, some sterilize completely, some leave survivors. Some are predictable, some random, some are natural, some human-caused. The sun's explosion in our thought experiment is unusual for being both fast and complete, eliminating all life in hours while leaving the planet physically intact. Most real endings are either slow, sun's death, climate change, or incomplete, asteroid impacts that cause mass extinctions but leave survivors, nuclear war, supernovae. Complete sterilization of Earth through natural means requires either the sun's death or an extraordinarily large asteroid impact. Both are far in the future, giving life billions more years if nothing else intervenes. This timeline, billions of years of habitability remaining, is important context for the thought experiment. We're not actually facing imminent extinction through cosmic catastrophe. The sun will continue burning steadily for 1 billion years before Earth becomes uninhabitable, and for 5 billion before the sun dies. This timescale is so long that it's effectively infinite from human perspective. But it's not infinite. Earth's habitability has an expiration date, as certain as death for an organism. The biosphere is temporary, will end, and will not return. This is guaranteed by the physics of stellar evolution. Even if life survives all other threats, asteroids, climate change, human recklessness, it cannot survive the sun's death without leaving Earth. This might motivate spacefaring civilization. If life is to persist beyond Earth's expiration date, it must spread to other worlds. This is possible in principle. Humans have already landed on the moon, sent probes to other planets, developed the technology for interplanetary travel. Interstellar travel is harder, but not impossible. Given billions of years, even slow generation ships could reach nearby stars. But this assumes civilization survives long enough to develop and execute such plans. Most civilizations might not. They might end themselves through war or environmental destruction. They might never develop spacefaring technology. They might develop it, but not have time to use it before some catastrophe ends them. The galaxy might be full of dead civilizations that never left their home planets. This is one possible solution to the Fermi paradox. If most biospheres end before becoming interstellar, either through cosmic catastrophe or self-destruction, then intelligent life might be common, but interstellar civilization might be rare. We might be alone not because intelligence rarely evolves, but because it rarely survives long enough to spread. Earth's alternative endings, then, provide context for existence itself. The thought experiment of the sun exploding tomorrow is impossible, but some ending is certain. The only question is which ending and when. This certainty of eventual ending applies to all biospheres, all civilizations, perhaps all conscious beings in the universe. How one responds to this certainty varies. Some find it depressing. If everything ends, what's the point? Others find it motivating. If time is limited, use it well. Still others find it irrelevant. The ending is so far in the future that it doesn't affect present decisions. All these responses are reasonable, depending on one's values and temperament. The thought experiment of the sun's explosion compresses the timeline, making the ending immediate rather than billions of years away. This compression changes the emotional valence. Distant doom is abstract, immediate doom is visceral. But the underlying truth is the same. Earth's biosphere is temporary, will end, and when it ends, will take with it everything that evolved here. This truth applies regardless of which ending actually occurs. Whether the sun explodes tomorrow, impossible, dies in 5 billion years, certain, or Earth is sterilized by asteroid impact in a few million years, unlikely but possible, the result is the same. The end of Earth's 4 billion year biological experiment. The timeline differs, but the conclusion does not. We exist in the middle of Earth's story, not at its beginning or end. Life arose about 4 billion years ago and has about 1 billion years of surface habitability remaining, maybe 5 billion before certain sterilization. Humans have existed for perhaps 300,000 years, a tiny fraction of this timeline. Human civilization is about 10,000 years old, a blink. This perspective helps calibrate our significance. We're latecomers to a process that started long before us and will continue after us, though not forever. We're not the endpoint of evolution, just one stage among billions. If humanity ends itself tomorrow through nuclear war or pandemic, Earth's story continues. Other species will evolve, perhaps eventually other intelligent species, until the sun's increasing luminosity finally ends all surface life. But from human perspective, our ending would feel like Earth's ending because we wouldn't be there to witness what comes after. This is the limitation of subjective experience. We can only observe while we exist. Our extinction would be the end of the world from our perspective, even if the world continues. The thought experiment of the sun's explosion creates a scenario where human extinction is literally Earth's extinction, where our ending and the biosphere's ending coincide. In reality, these are likely to be separate events, separated by millions or billions of years. But the thought experiment collapses them into simultaneity, making human mortality a mirror of cosmic mortality, making personal endings reflect universal endings. This mirroring is part of what gives the thought experiment its power. It connects human-scale concerns with cosmic-scale processes, showing that the same pattern, existence followed by cessation, applies at all scales, from individuals to species to biospheres to eventually the universe itself. Everything that begins ends, and understanding one ending helps understand all endings, whether fast or slow, near or far, personal or cosmic. The eternal recurrence. One final perspective on Earth's hypothetical death comes from considering cyclical time rather than linear time. The physicist's view of time is that it flows in one direction, from past to future, with events occurring once and never repeating. Earth forms, life arises, evolves, ends, and that sequence occurs once, never to be repeated in exactly that way again. But some philosophical and religious traditions conceive of time as cyclical, with patterns repeating over vast timescales. The Hindu concept of kalpa, the Buddhist wheel of dharma, the Stoic eternal return, all imagine existence as cycling through creation and destruction repeatedly, perhaps infinitely. In this framework, Earth's death is not an ending but a transition to a new beginning. The universe might collapse and Big Bang again, or multiverse theories might suggest infinite parallel worlds where Earth exists in all possible states simultaneously. Or quantum mechanics might allow for closed time-like curves where events loop back on themselves. These cyclical conceptions are not mainstream physics, but they're not entirely ruled out. The universe's ultimate fate depends on its geometry and expansion rate, both of which are still being measured. If the universe eventually contracts in a big crunch, it might bounce and expand again, creating a new universe with new galaxies and stars and perhaps new Earths. Even in linear time, patterns recur. Stars form, burn, die, and their matter seeds new stars. Planets form around these new stars. Life might arise again on these new planets, evolve again, develop intelligence again. The specific details differ, new species, new histories, new names. But the pattern is similar, complexity arising from matter, consciousness emerging from complexity, civilizations building on consciousness. In this sense, Earth's story is not unique but typical. What happened here has probably happened on countless other worlds, and will happen on countless more. The specific arrangement of atoms that was Earth and its biosphere won't recur, but similar arrangements will. The universe repeats its patterns without exactly repeating its specifics. This provides one kind of comfort in the face of Earth's hypothetical death. If consciousness arises repeatedly across the universe, if the pattern of life and intelligence is common even if each instance is unique, then Earth's ending doesn't eliminate consciousness from the universe. It eliminates one local instance while leaving the general pattern intact. But this is cold comfort for those experiencing the ending. The fact that other consciousnesses exist elsewhere doesn't console someone facing death. The pattern continuing doesn't help the individual instance that's ceasing. This is the limitation of abstract philosophical comfort. It works intellectually, but not emotionally. Still, the cyclical or pattern-based view highlights something important about existence. We are instantiations of patterns, not unique creations. The specific atoms in our bodies were once parts of stars will eventually be parts of something else. The patterns those atoms form, our bodies, our brains, our thoughts, are temporary. But the possibility of such patterns, the fact that matter can organize itself into consciousness, is a feature of the universe that persists beyond any individual instance. Earth in our thought experiment dies, but Earth-like planets exist elsewhere and will continue to form. Life ends on this planet, but lifelike processes might occur on countless others. Human consciousness ceases, but consciousness as a category, as a phenomenon that matter can exhibit under certain conditions, remains possible wherever those conditions occur. This suggests a kind of immortality, not of individuals or species, but of patterns and possibilities. The specific organisms that lived on Earth are gone forever, but the possibility of organisms remains. The specific intelligences that evolved here have ended, but intelligence as a capacity of complex systems persists as a latent property of the universe, ready to manifest whenever conditions allow. From this view, death is not the opposite of life, but its complement. Both are necessary for the pattern to continue. Life creates complexity and consciousness. Death creates the conditions for renewal and new beginnings. The cycle requires both phases. There cannot be new life without old life ending and releasing its resources. On cosmic scales, this cycle is clear. Stars die and seed space with heavy elements necessary for planets and life. Planets die and their matter eventually forms new planets. Life ends and makes room for new life, sometimes through extinction events that open ecological niches for new radiations. Death enables life in the long view, by making resources available for new configurations. This doesn't make individual deaths less tragic. The organisms dying when the sun explodes in our thought experiment don't benefit from the knowledge that their constituent atoms will eventually be parts of something else. Death remains death from the inside, regardless of what cosmic recycling might follow. But it does provide a framework for thinking about endings that's less focused on loss and more on transformation. Earth's death in our scenario is the transformation of an organized system into a less organized system, a local decrease in entropy at the cost of increased entropy elsewhere. The matter persists, the energy persists, the possibilities persist. Only the specific arrangement ends. This might also inform how we think about our actual, non-hypothetical relationship with Earth and its future. If we recognize that we're temporary instances of patterns that will recur, we might feel less pressure to preserve exactly what exists now, and more freedom to allow transformation while protecting the conditions that allow patterns to continue. In practical terms, this might mean accepting that specific species, ecosystems, even human cultures are temporary while working to preserve the conditions, habitable climate, intact ecosystems, stable civilization, that allow new patterns to emerge. It's a balance between preservation and acceptance of change, recognizing that some change is inevitable and even necessary while some changes are catastrophic and should be prevented. Earth's hypothetical death in our scenario is clearly in the catastrophic category. It prevents any further patterns from emerging on this planet. But Earth's eventual actual death in 1 billion years is in the inevitable category. It cannot be prevented without moving Earth or leaving it. The distinction between catastrophic and inevitable changes is important for deciding how to respond. Catastrophic changes should be prevented if possible. Inevitable changes should be accepted and adapted to. The difficulty is distinguishing between them. Some changes that seem inevitable might be preventable with sufficient effort, and some changes that seem preventable might actually be inevitable given physical or practical constraints. The thought experiment of the sun's explosion is useful here because it's clearly impossible, making it purely hypothetical. We don't have to worry about preventing it or adapting to it. We can simply use it to explore our reactions to ending, to practice thinking about catastrophe, to calibrate our responses for actual risks that are neither impossible nor certain. In doing this exploration, we discover something about how we relate to existence. Do we cling to specific forms and arrangements, grieving their loss? Do we focus on patterns and possibilities, finding comfort in continuity at higher levels of abstraction? Do we embrace each moment's uniqueness without worrying about what comes after? Each approach has merit, and individuals will find different approaches more or less appealing based on temperament and philosophy. The eternal recurrence as conceived by Nietzsche offers yet another angle. He imagined being willing to live one's life again, exactly as it was, infinitely many times. This is not a cosmological claim, but a value criterion. Would you live your life in a way that you'd be willing to repeat it forever? Applied to Earth's story, this asks, was Earth's existence valuable enough that it would be worth repeating, even including the suffering and death? From within the experience, the answer is unclear. Suffering is real, death is real, and they don't feel justified by the existence that preceded them. But from outside, looking at the whole pattern, the answer might be different. Earth created 4 billion years of diverse life, including consciousness and intelligence. Is that valuable enough to justify the suffering and death that accompanied it? This is not a question with an objective answer. value is assigned by conscious beings, and different beings will assign it differently. Some find life's value sufficient to justify its costs, others don't. The thought experiment doesn't resolve this, but it makes the question explicit and unavoidable. If we imagine Earth's existence recurring eternally, forming, developing life, evolving consciousness, then being sterilized by an exploding sun, then the pattern repeating, would we affirm this cycle? Would we say yes to Earth's existence even knowing how it ends? The question applies not just to Earth, but to our own lives. If we knew that our lives would end suddenly and perhaps painfully, would we still choose to have lived? Most people, asked in calm moments, say yes. Life has value despite its ending. But this is easy to affirm in the abstract, harder to maintain when actually facing the ending. Earth's hypothetical death forces this question to a cosmic scale. Does 4 billion years of life justify the ending? Does the existence of consciousness justify its extinction? Does the beauty and complexity that evolved justify their destruction? These questions have no universal answers, only personal and provisional ones that each consciousness must answer for itself. In the end, the eternal recurrence is not literally about repetition, but about affirmation. Can we affirm existence despite its contingency, impermanence, and eventual ending? Can we say yes to life knowing it will end? Yes to consciousness knowing it will cease? Yes to meaning knowing it will be erased? The thought experiment of the sun's explosion tests this affirmation. If Earth and all its life died tomorrow, having existed for 4 billion years, would that existence have been worthwhile? Would the pattern have been worth instantiating despite its terrible ending? Would we do it again if we could? These questions remain as we close this journey through the impossible. The sun will not explode tomorrow. Earth will not die in the way we've imagined. But the questions the imagination raises are real and worth contemplating. How do we live with awareness of ending? What do we value knowing it's temporary? How do we affirm existence despite its fragility? The answers, if there are answers, lie not in the thought experiment itself, but in how we respond to it, how it changes our perspective, and whether we can return to our actual lives with greater appreciation for the impossible improbability that we exist at all, that Earth exists, that the sun burns steadily, giving us one more day, one more chance to witness the universe's brief experiment in consciousness before it ends, as all things end, in its own time. The question that remains: what if the sun exploded tomorrow? We have followed the answer through its implications. 8 minutes of unknowing, then light that kills, heat that sterilizes, bombardment that reshapes, cooling that freezes, and finally, an eternity of frozen wandering through the dark between stars. The sun will not explode tomorrow. It cannot. The physics of stellar evolution prevents it. Our star is a yellow dwarf, stable and middle-aged, with billions of years of steady burning ahead. We can rest certain in this knowledge, as certain as we can be about anything in a universe that occasionally surprises us. Yet the question remains valuable, not for its realism, but for what it illuminates about existence itself. By imagining the impossible, we come to understand what is, the delicate balance that makes life possible, the narrow range of conditions that separate habitable from hostile, the profound contingency of everything we take for granted. We assume the sun will rise tomorrow because it has risen every previous tomorrow in human experience, in the experience of every organism that ever lived. This assumption is reasonable. The sun is remarkably stable, its fusion regulated by natural feedback loops that have kept it burning steadily for 4.5 billion years. Yet our certainty is based on observed patterns, not on necessity. The universe is not required to maintain the patterns we observe. It simply happens to do so, and we exist in a moment when the patterns hold. The thought experiment of the sun's explosion strips away the comfortable assumption of stability. It forces confrontation with the fact that life exists in a narrow envelope of conditions, that Earth orbits in the habitable zone by chance, that the elements necessary for life were forged in previous generations of stars, that everything that makes existence possible emerged from prior events that could have been different. What remains after contemplating this hypothetical catastrophe is not fear, the sun will not explode, but perspective. We live on a planet that is, for now, in precisely the right conditions for life. We orbit a star that is, for now, remarkably stable. We exist in a time when complex life is possible, between the period when Earth was too hostile for life and the future when the Sun's death will make it impossible again. This time is finite. Not finite in the sense of days or years, but finite nonetheless. In 5 billion years, give or take, the Sun will expand into a red giant and will likely engulf Earth. Long before that, perhaps in 1 billion years, increasing solar luminosity will have made Earth too hot for liquid water. The habitability of our planet is temporary, bracketed by periods when conditions do not permit life. But for now, for this cosmic instant that encompasses all of human history and will encompass thousands or millions of years more if we avoid destroying ourselves, conditions are right. Water is liquid, the temperature is moderate, the atmosphere is breathable, the Sun is stable. We exist in a moment of balance, unlikely and temporary but real. The value of asking, what if the Sun exploded tomorrow, is that it throws this moment into sharp relief. We might take for granted the Sun's constancy, the Earth's habitability, the continuation of patterns we've always observed. The thought experiment reminds us that these are gifts, not guarantees. Phenomena that happen to occur and could, in principle, cease, though the Sun's explosion is not among the ways they will actually cease. What does one do with this knowledge? The recognition that existence is contingent, that the conditions for life are specific and temporary, that everything could theoretically be different. Perhaps nothing. Perhaps everything continues as before, with the added awareness that continuation is remarkable. Perhaps the sunrise becomes slightly more beautiful when recognized as something that need not happen but does. Perhaps the breath becomes slightly more precious when understood as depending on a chain of causation, stretching back to the formation of the solar system and forward to the Sun's eventual death. Or perhaps the knowledge changes perspective in more substantial ways. If existence is contingent and temporary, if life depends on conditions that are special and will not last forever, perhaps the appropriate response is to appreciate what exists while it exists, to be attentive to the improbable marvel of consciousness arising from matter, of intelligence emerging from evolution, of a species that can contemplate its own existence and ask questions about hypothetical catastrophes. The Sun will rise tomorrow and the day after, and for billions of days beyond counting. We can return to our lives with reasonable certainty that the patterns will hold, that the balance will persist, that the conditions for existence will continue. But we might return with altered perspective, seeing the ordinary as extraordinary, recognizing that the backdrop against which we live our lives is itself miraculous in its stability and suitability for life. The question, what if the Sun exploded tomorrow, ultimately points back to the reality that it will not, and in that negation lies a kind of gratitude, not to anyone or anything, but simply gratitude as a stance toward existence, recognition that the universe has arranged itself in such a way that we can ask such questions at all. In the dark between stars, frozen Earth wanders, carrying its cargo of ruin and memory. But here, now, on the actual Earth that orbits an actual Sun, life continues, the patterns hold, the balance persists, and in that persistence is something worth contemplating, not the disaster that will never happen, but the ordinary miracle of another day, another sunrise, another moment of existence in a universe that could be otherwise but for now, is exactly this. The Sun burns on, as it has burned, as it will burn, constant and indifferent and absolutely essential. And we, improbable assemblies of stardust temporarily organized into consciousness, witness its light one more time, grateful for the impossible possibility that brought us here, aware of the contingency that sustains us, and mindful that this moment, this brief window when Earth is alive and minds exist to wonder about it, is precious precisely because it is temporary, specific, and unfathomably unlikely to have occurred at all.